From the top, it's a toggle.
Okay, perfect.
Okay. And then when you're ready to go, I'll turn.
Test. So we actually have to wait until someone comes in to start the stream. So keep talking, commenting on the picture. Okay, I'm assuming the thumbs up means that we're good to go. Welcome, everybody. This is a update from last year on Rust on Zephyr with an obligatory DALL-E slide with a nice logo for Rust and Zephyr, or the other one it generated the first time. I don't know what that's supposed to mean. So last year, I gave a talk, it was either last year or the year before, I'm fuzzy on that, about Rust on Zephyr. And at that talk, I presented the wonderful program of Hello World. I got a small Rust application with main that ran as a Zephyr application, and it printed a message over the console. It's very manual, lots of issues with linking and the conflicts with LLVM and GCC and all that kind of stuff. So what's happened in the last year? So just kind of as an overview, I will show some pictures. Just after that conference then, I got infected with the build your own keyboard virus. And so I've been making a couple of these things. This was called Proto 2, or Proto 3 for lack of a better name. And Proto 4 is my current iteration. You'll notice a theme with the number of keys. These are either 30 or 42 key split keyboards, various layouts. They have onboard steno translation with the dictionary. It's like a little over 4 megabytes with all kinds of fun, exciting algorithms that I would never want to try to implement in C. The code does scanning, debouncing, chord modes, USB, all this stuff. And I started with QMK, like a lot of people do. It didn't take very long to get firmware running with QMK, but I wanted to do it in Rust. So I started writing my own code with Rust embedded, working with some of the people behind that. And it works. Started running into a lot of issues with the HAL support and Rust embedded is kind of mixed bag as far as how good it is. I'm like, you know, I also work on Zephyr. I did Rust on Zephyr. This might be a good combination. So I moved the keyboard firmware to be written in Rust, running on top of Zephyr. And we'll get to in a minute why it's not something I don't mind sharing it, but it's not something that's usable to anyone yet. But so my firmware right now is about 5,900 lines of general Rust that didn't change when I moved it from Rust embedded to sit on top of Zephyr. By not changed, there was less than like 10 lines of code that had to change for various things. There was like, I don't know why that's such an exact number, but like 1,600 and some lines of code with comment, it's not slot count, of Rust embedded specific code. Most of that living in a file called main.rs, and it's really fragile, was the thing I discovered about Rust embedded. It doesn't really handle the idea that I want to work on multiple targets. And we get spoiled in the Zephyr world that you can say West build and pick a different board and your code just works on a different board. With the way Rust embedded, your main has all these things in it, and like the GPIO pins each have their own type. And so when you want to declare a variable that holds one, well, that changes when you change different targets because they're on different GPIOs. And we'll see where that goes, because somebody's going to have to figure out that, oh, we want this to actually be useful, so rather than strongly typed. So I don't know where that's going to end up. But so I ended up writing about 2,600 lines of code to make this thing work on top of Zephyr, along with like 500 and some lines of C code to glue it together. But the important thing is that there's only 1,300 lines of code that are for the keyboard, and those were mostly copied from the Rust embedded code. That was some of the matrix scanning code and stuff, because it's directly interfacing with drivers is a bit different. The rest of that code is the Rust on Zephyr support code, which is still embedded in my keyboard firmware. But what I'm going to talk about today is how do we go forward with this so that Rust on Zephyr is a thing people say, oh, I want to do that. And they can go do west build, set a board, and then just point to samples Rust such and such and build it. And that it not be 1,500 lines of code in that thing. So I made an RFC, I don't know, 3 or 4 months ago. You can go look at this. The goal of this RFC is application development on Rust. People are always like, when can I write drivers in Rust? And the simple answer is this is step 1, that's step 3. So we'll get there, but that's not the focus here. This should be in the Zephyr tree. The goal is that you should be able to do Rust up, get a stable Rust compiler, have your Zephyr tree that you just built, that you just got, and build a Rust application on top of Zephyr. It should feel like you're writing Rust code. I know there's people that are writing Rust on Zephyr now, like me, and you end up with a lot of these little wrappers and lots of unsafe sprinkled all over your code. And that's not what we want here. This should feel like writing Rust code. It should feel, when you want to do a channel, when you want to do a mutex, it should feel like you were using the one in standard, just it happens to work on top of Zephyr. So how do we get there? What's involved? And what I will say is that my tree is a hack, my firmware, to figure out what are all the steps and pieces we need to get there, and then work will be making this clean and putting it in the upstream tree. So how do we build this? If you're familiar with Rust, Rust has this thing called cargo, and it runs the world. You have a program, you build it, you type cargo build, and you get an executable. You type cargo run, it runs it. You type cargo test. It's really nice. Zephyr has the same idea. You type west build, you type west flash, you type west different things, and you get your build. How do we mush these things together? So the cargo system has one little thing that you can do, and you can tell it to build a library. And it will do all its magic, and then it will generate a .a file buried in some directory, but that's fine. So we're going to let cargo do that. But it needs to know a bunch of things that came from CMake as far as Zephyr builds. When you do a build, what is the target? What Kconfigs are set? There's all kinds of stuff going on there. So there's a bunch of pieces here. So what happens, and what have I got working here? So there's a CMake mapping between Zephyr's idea of build targets, which is done through a combination of, it's Kconfig entries set by a board and possibly an SOC and some other things that decide what target you're actually on. In Rust, it's an LLVM target name. It's a triple of, or 4, of strings separated by hyphens that tells it exactly the configuration CPU that you're building for. We also have some crates that are going to be Zephyr specific. There's a Zephyr sys, there's going to be a Zephyr, there's going to be some things with device tree and Kconfig that we want to own as the Zephyr. We want those to be part of the Zephyr. They're going to be modules. And so we need to add these path overrides so it doesn't go try to grab these from cargo. There's also some issues with, if we have dependencies, the project policies of Zephyr are going to require that we vendor those. And so we want to be pointing to the vendored versions of those. And a couple other things is, if you just go into my directory right now and haven't set this up and you type cargo build, it will spew all kinds of garbage out because it's trying to build for your host and doesn't have Zephyr packages and all this stuff is missing. So one of the goals was to generate a template for the .cargo/config.toml so that you can just type cargo build. It won't make an executable. It will just do the part that cargo is doing. But importantly, your IDE will just magically work at that point. And you can, do function completion. You can go look at other code in different crates and everything. Some other things is the CMake lists file in your Rust application. It should be small. If you look at some of the sample ones right now, they're usually 4 or 5 lines of actual CMake stuff, and several of those are just required by CMake. And we want something similar that's like, oh, I have a Rust application. Here we are. So what are the details? This is where I've learned more about CMake than I thought I would need to know and kind of want to know, but I had to learn this. So there's some things in here about, this is an example just for the Cortex-M of you picked a target on Zephyr. What do you pass to Rust as far as the Rust target? As you can see, there's a lot missing here. This won't just run on ARM, but we want it to run on the Cortex-M. Oh, and then there's a fun comment in there about the ARM v7, ARM v8, FP tag in there. So I mentioned that .cargo config. Here's the CMake, part of the CMake fragment that builds that. This just writes a file. It's in the build directory, so you'd have build, and then this would be build / I forget the exact name I called it, and you can actually just symlink that to be your cargo config, and then things work for you. There's a custom command that, based on, this was the not fun part of CMake to figure out. CMake was very, very upset with the idea that I had a command that I need to run, and I need to always run that command, and it has a whole bunch of things that it knows that we don't need to tell CMake about. And so it turns out the way you do this is you make it depend on this dummy file that never exists, so it always tries rerunning it. And then you say, oh, and as a byproduct, we produce the .a file. So this runs cargo. And all these lines that you see here are the same things that are in the .cargo config. So in a sense, they're redundant, but this means that CMake can build it before you actually symlink that file, because otherwise there's this kind of catch-22 problem. So with all of that, and this won't live in your tree. This is going to be off in a CMake function that you would just call from your CMake file. But this allows this whole process of, so what happens when you do West build? CMake does a whole bunch of stuff. It figures out, it runs Kconfig, it generates a bunch of files, all this stuff. Then it gets to where it needs to do things. It compiles some of the Zephyr code, then it runs cargo, and it compiles some of the other Zephyr code. The ordering there is not, I mean, I'm sure it's deterministic, but it's not determined, if that makes sense. And what you end up with is it runs cargo in the middle of your West build, and then you get an application, and you can run it. So, Kconfig. This is very different than what Rust thinks. Rust likes the idea of you have features, and they live in your cargo.toml file at the top of your source tree or project, or some different options there. And Zephyr has its own idea. It has this thing called Kconfig. There's all these configurations. There's dependencies. It's vastly more complicated in use than is typically done with features in Rust. So the thing about Rust is there's kind of some definitive things. In C, we can have pound defines that we if-def on, and you can have source files that change what's defined. So we have header files that might define more things, that might conditionalize. Rust has a kind of policy in the project that the compilation of the conditional compilation cannot depend on anything set by the source code in the project. So these configuration options, if we want them to be visible to Rust code, they have to come in as we run cargo. So what do? The idea, well, let's just look at what's going on here. So there's a program that runs as part of a Rust build. And this won't actually be visible to you using it unless you need this conditional compilation. Otherwise, it just happens in Zephyr sys, and it knows how to conditionalize. But the idea is that this reads the generated build/zephyr/.config, or if you're using sysbuild, whatever that it ends up, and it looks through the config options. And there's two things it's looking for. It's looking for Boolean ones, and those become what are called, I don't know how you pronounce it, CFG things in Rust. And so in my Rust program, I can say #CFG config foobar, and have a piece of code that's conditionally compiled in Rust based on a Kconfig setting that came from Zephyr. The other ones are things that are Kconfig settings that are strings or numbers and those kind of things. And those get turned into consts in Rust. So these don't generate code, but you can refer to them as either numbers or they're kind of static strings. So that's Kconfig. And when implementing this, just as a caveat, much of this is speculative. So when we get to actually implementing it, things may change, or we get feedback when we post patches and that kind of thing. So that's Kconfig. It's actually the easy one. And we have the device tree. And if you've done Zephyr, you know the device tree is a pretty integral part of how it works as far as configuration, boards, everything about a given build. Much of that is defined by the device tree. So, yeah, did you? Sure. There's not a microphone, but I can repeat your question.
Are we going to get the same wonderful error message about device tree?
I'm hoping to have worse error messages with no. So I'll get into why that. The question is, if you've ever tried to use the device tree from C in Zephyr, and if you get something slightly wrong, you get a 5,000-line error message, not quite, but you get a whole bunch of errors about macros. So the way this works is there's code that runs that reads the device tree. So it generates it's not a flattened device tree. I don't know what we call it. It's a device tree that's canonicalized. It doesn't have any conditionals in it. It's been through the C preprocessor. And then we walk through that based on a bunch of YAML files that describe what is allowed in the build. And then we generate this file by stitching names together of the tree. So the device tree is a tree. That shouldn't be surprising. And we stitch the node names together with conventions. Kind of similar to how you might make variable names in a language like Rust or C++, where you have modules. But the linker needs to see them, and we don't do it with Z's and numbers, but we do it with I think they're just like underscores, and we have an N for the root and that kind of thing. Needless to say, that's not a really good solution for Rust. If anything, the ability to stitch names together in a macro is an unstable feature. And one of my goals is to try to avoid needing to depend on unstable. But in Rust, we have modules. It's a hierarchy of names. It maps really, really well to the device tree, which is a hierarchy of names. So let's just make that. We have a device tree. We have a module tree. Why not make them one-to-one? So what do the things in the device tree end up with? Because I talked about, we don't want to generate code or stuff that takes up space in the target from the device tree. We want it to be things that are available at compile time. And then, obviously, if there's things in there that are needed as structures that need to be in the code, they will be. But it's not going to be this big data structure that represents the device tree. So there's a lot of things that are just consts. The device tree has a lot of numbers. But there's a lot of other things in there that are kind of weird, honestly. The properties are actually In the device tree, they're just byte arrays, but we don't use them that way in Zephyr. We interpret them before it's compiled down to this flattened device tree. So we actually have like groupings of properties. We have like if you have a GPIO definition, you'll have a P handle and a couple of numbers, and then a P handle and a couple of numbers. And we don't want to have a data structure with that in there that's going to expand in anything. So what I've been doing to start with is using const functions that can return that information. And it works kind of like a macro in C, where it doesn't actually generate code. It's expanded at compile time as needed, but it's still accessible and it's still usable. And if somebody does need it, it could generate code. Like if you needed a function pointer to one of these things, then it would be available. The other thing is the device tree has these things called aliases. You can have, like there's a chosen node, which is just a bunch of names that point to other nodes. And the way we do this or the way that I've started doing this, is you have a module, and then you have this construct in Rust where you can say pub use this other module, : asterisk, and it says, bring all the symbols from that module into this module, and then export them publicly. And so it's kind of exactly what aliasing means, that you now have visibility. So in your code, you'll be able to just refer to device tree, chosen, UART, or console, or whatever we had to figure out the name mangling because you can't have symbols with commas in them. But there'll be a convention. It'll probably be like Zephyr _ console. So what does this look like? Well, this is I'm forgetting the name of it. It's a parser generator. It's a PEG parser generator inside it's a Rust crate. And then this is a snippet of code, of a description of the device tree source file that this thing then parses, and it generates something kind of like this, with the caveat that I've only done a few of these, that a lot of them just turn into strings that are just then what was in the device tree. So you have things like, the hash address cells from the device tree turns into this N address cells. The compatible is a const function that returns a 2-element array of strings. And the way this works is if you call that function and then dereference it with like a 0, all of that goes away and you just have a string that ends up in the code. And then more and more. So there's a lot more to that. The thing I mentioned with the labels, for example, every node can have a label that refers to something deep in the tree. And so there will be a module that is the labels, that's each one of those is a module that has all of the names in it, so that you can just refer to something in your code by label. This is very similar to the device tree accessors in C, except they're just modules. The nice thing is all of this is visible to your IDE. So when you're in there writing code and you go Zephyr, figure out the names, I type Zephyr : device tree, I can start completing on the things that are in the device tree for my current build, and they're just there. All right, let's take a 5-second break because there was a lot with device tree. Okay, syscalls. I'm also kind of way ahead, so we'll have time for some questions here. So, oh goodness, a number of years ago, we added user space support to Zephyr, where we separate between threads that can be marked as user space threads and then the kernel mode. And in order to get into that mode, you have to make syscalls. And this was done not by drastically changing everything, but by basically going through the headers and marking a bunch of these functions as syscalls. They then don't actually generate, so they're headers, the real function gets a different name. Magic happens with Kconfig options as to whether you even have user space. Different code makes a dynamic decision as to whether you're a thread that is in user space or kernel space, either calls the function directly or does a trap to a system call. The short form is there's a bunch of code that reads the header files, looks for these syscalls, generates this table of the actual implementations. Importantly, there's no C function for me to call from Rust So I can't just say x turns c, this function, it doesn't exist. And so for my keyboard firmware, I have wrappers for all the syscalls I need. And I think I have a picture of that. Yeah, that's this. You have, sys mutex lock takes these arguments, and it calls k mutex lock. And then depending on how you're configured, that may just be the function, or it may expand inline to this kind of syscall check, which checks if we're syscall and then either calls the function or does the other things. So we're generating this kind of C-ish code by reading headers. And I think I want to do the same thing in Rust. Now, I haven't done any of this yet, so this is completely speculative. But we want to generate a Rust module that has all of the syscalls that are in your particular configuration with the syscall numbers that you ended up with, because as we discussed in a different meeting, those change depending on your build. And you have this module that now you can make syscalls from Rust, and they should have exactly the same overhead as they would in C. The syscalls will be expanded inline. They will do the check. Depending on your configuration, they may just directly call the implementation, or they may check if you're user mode and do the trap as necessary. Now, the interesting thing is they're all unsafe as far as Rust is concerned. You're calling C. We don't have any guarantees. There's pointers all over the place. None of this fits Rust's model of safe pointers and that kind of thing. So this goes into something that's traditionally called like Zephyr sys, where it's an implementation that then there's wrappers on top of. So we want to build above that abstractions. So in the Rust standard library and a bunch of support crates, there's something called parking lot, which is a cleaner implementation of communication channels. There's mutexes, mutexes. I don't know quite what the right word for that is. But I want to build abstractions that look like the ones in standard. Just as a caveat, I say, why don't we just implement standard? Somebody's actually done that. There's an implementation. To use that, you grab all of LLVM, the source code to the Rust compiler for an exact version that they support. You mush all of this together, you build it, and hopefully you get a tool chain that has standard that might work with some specific version. Aside from the fact that I don't think it's actually the right solution because we're not a POSIX system. We have some POSIX-like stuff, but there's a lot of stuff we don't have. And I think it makes more sense to provide the abstractions that make sense on Zephyr, just in a module called Zephyr instead of standard. It also has the advantage that you just use regular tools to build this. You don't have to go build a tool chain, because I think that would block adoption of this, that if people have to build a Rust tool chain as well. So what do we do for abstractions? So most of the Rust abstractions assume that the underlying operating system primitives can be dynamically allocated. pthread create, that kind of thing. So a lot of them in Zephyr can be allocated, but you don't want to do that, at least unless part of this project is about making dynamic K objects more efficient, because the statically allocated K objects go through a perfect hash function for lookups for validity. Dynamically allocated K objects are in a linked list that it scans every single time you use one. So they're useful if you have a few system-wide. They're not useful if you have a large number of them. So some of the solutions are to have like pools of these that are allocated to fix the allocator. That I don't have the correct answer for that yet. The other thing is there's a couple of K objects, like the most useful ones, including sys, mutex, and futex, that cannot be allocated dynamically at all. So that isn't even an option. And I mean, it's literally if, when in the K object allocate, there's an if statement, and if it's one of these two, return an error. It's because there's a user space and a kernel allocation together, and there's not been any code written to manage that. So there's a lot of choices behind this. We can have clean Rust APIs on these wrappers and end up with these things that aren't compatible with C code, or we can have less safe APIs, but then compatible with C code. And I honestly think the answer is that we're going to probably need both. That there will be times where if you're using a library in C that needs a mutex, that needs a FIFO, or some kernel data structure, you're going to have to use that kernel data structure from Rust, and there's probably going to be some unsafe involved. But if you're writing an application that's just in Rust, and you don't need to interface with C code for some of these things, it'd be nice to have these data structures that work like they would in other Rust code. There's no unsafe, I just allocate them, I lock, I do that kind of thing. So I'm guessing we'll need both. Little snippets of the implementation here. We have, and by the way, by implementation, I mean my hacked together thing so that I could do mutex, not one that everybody would want to use. But this is kind of the messy code you don't want to see. But the end result of this is we have this thing called a mutex that wraps around a piece of data. This is kind of the Rust thing that differs, whereas in most C things, you have a mutex, it's a thing, it lives by itself. And then hopefully you keep track of what data goes with it. In Rust, the mutex wraps around the object that it's protecting, and you can't get to that thing unless you lock the mutex. So that's where it gets the additional safety from. It's also why that thing that it's wrapping has to obey Rust's notion of ownership, can be moved with its rules and that kind of thing. But that's all doable. We can do that with the, I mean, this works. When I press keys on my keyboard, there's a mutex around a queue that's keeping that data, and it all works. So, getting near the end here of this, drivers. Now, drivers and device tree are kind of intimately tied together, so the data about given drivers is going to have to come from the device tree, and there'll need to be abstractions, whether these are like macros or functions that are generated, that kind of thing, I'm not really sure. But then you get this device back, and in Zephyr we have a struct device. And all devices are generally a struct device. There's a few like GPIOs that are a wrapper with a struct device in it and then 2 integers to tell you which pin and that kind of thing. But most part, it's a struct device. If you go get your UART, you get a struct device back and you call an I2C method on it, you probably will segfault or something really awful. It's not strongly typed or anything. And in Rust, we'd like these things to be typed so that the methods on the device are methods on the particular struct. So this is going to be a good amount of work. I mean, my goal with this is to start with some subsystems, but realistically, I think this is where hopefully the community starts to get involved and somebody says, I want this device. And there's a lot of things that have to be figured out. The devices are kind of different. There's still a lot of stuff that's built around callbacks, which is hard to do safely in Rust. It can be wrapped, but there's also this kind of move to make, those don't usually work from user space either, is the issue. So it's kind of ad hoc, and there's a lot of case by case is what it comes down to. What I did is basically, I have the sys wrappers for the device, the actual calls that are there, because they're system calls. And then I'm wrapping the device, the struct device, in a GPIO struct, in this case, that has methods on it. So in the Rust code, I can say, set, clear, toggle, the different things that map to these functions here, configure, and I just use them and there's no unsafe involved because the type system made sure that that's the right thing where that makes sense to call. But this is a big part of the work to do this. So the last thing I want to talk about here is logging. And Zephyr has a fairly rich logging system. Well, actually, Zephyr has several fairly rich logging systems, and you pick an implementation that you'd like. What I'm doing right now, just to make it work, is when you do a log message in Rust, it mallocks the end resulting string. It just uses format, and then that's passed in through a C wrapper to log that into Zephyr, and then it gets freed. It's this kind of automatically happens, but it's not very efficient. And so we have to think about Zephyr's doing log messages with formatting, but it's printf. You know, it's %d. It's its own specific style of printf formatting. So what do we do? Rust has its own thing. They use braces. It looks more like the Python one. There's different indicators. Most embedded things in Rust have restricted subsets of them, so that's certainly an option. But one option is, should Zephyr's logging mechanism support pluggable formatting for the delayed formatting so that the Rust logging could do it in a similar manner, where here's a format string, and some arguments, and then that gets generated when the log messages go through. Another option is there's a package for Rust called Definite. I don't know how you pronounce that word. It is a host deferred formatting. So when you say log, or warn, and then you have a string and you have some arguments, the string never makes it into the executable at all. And what gets logged is an index and your arguments. And then there's a host side program that pulls that down, expands the string. It works really well until you forgot to stop it and restart the little host daemon, and you're out of sync and your strings are nonsense and you get really, really weird messages. Again, I don't know the right answer to this, but there's a lot of possibilities. I mean, ideally, we want it to be low overhead and work with the existing Zephyr logging. What I do now is I have macros that work like the log crate in Rust. So you have a macro called error that takes formatting arguments and it logs it. And what I do is I call alloc format. I put this into a string, and then I pass this off to this C wrapper that I wrote called log message, which just spews the message, queues up the message in the Zephyr logging system. So this is like, if you picture how I've moved in my code from clean to complete hack, this is the most hack aspect of it all. So that's it for what I wanted to share with topic. And we've got, I think, about 3 minutes left for questions and that kind of thing. So, and I see like 37 hands, so Brix, you've got some work to do.
So I have one question out of curiosity. Why enable user space? What is it necessary?
No, but
okay.
It feels wrong to not let it work. I mean, I guess it's part of it.
Okay.
So the question about why user space, because I think there is still reason for it if your application. So one reason to not need user space is, well, we're writing Rust code, it's safe. But maybe that's not the only code that's on my system. Maybe there is also other user space things, and I still want that separation. So I think it should work still.
So are you using the Rust standard library? And you mentioned using crates, so that's
No standard.
No standard. Okay, thank you. So you're doing classic embedded Rust, basically.
With alloc.
Okay, and then what are the size implications, like in terms of the .a that's now being built in? Were you seeing any size constraint issues? Because we tend to care about that a lot in Zephyr, or not?
Yes and no. I mean, I'm thinking a little bit about it. The problem is my builds right now, I'm pulling in like format, and that tends to overwhelm all the rest of the system with, I had one thing where I'm on a no hardware float point target, and I did a little bit of floating point math to print out a nice number for a log message, and it added like 35K to my application. So I haven't actually started looking at that yet. Yeah, there's definitely some concerns with, does Rust make everything big? But if you're careful, it doesn't have to make it that bad.
I was just wondering, do you use anything like bindgen, or are all these wrappers manually written?
So I'm not using bindgen currently. And that's kind of a big question. Like the syscall thing is going to be bindgen-like, and I don't know if that will be our own version of bindgen that knows how to do that, or if it's flexible enough to do that. But yeah, there's all kinds of structs that are full of if-defs and stuff, and that we do need to map, and it'd be nice to not have to maintain that by hand. So, but I don't know if that answers the question. Basically, I haven't looked at it yet, but it might be useful.
Could you use a combination of pinning and repr-c to hold those mutexes in Rust and still pass them to C safely?
So currently, no. I mean, yes, I use repr-c, but right now, all of the things that Zephyr needs to know about that need to be at specific addresses have to be statically allocated. And so currently, my implementations, you have to pass in a const star thing to it as part of this unsafe init. And it's a problem we'll have to figure out how to solve, whether there's pools, whether we do get some kind of dynamic allocation, but they're special and magical from Zephyr's point of view. They happen to be pointers, but they're better thought of as abstractions, as just bits from Rust's side. We don't get to allocate them. They're not in memory that's visible to us. Their handle happens to be their address in Zephyr memory, so.
Great talk, David. Couple questions for you. So,
Sure.
I guess, have you looked at, so Zephyr has many struct objects, right? It's just a bunch of function pointers. Have you looked at how Linux deals with that, with, proc macros to sort of, match those things up well?
Not yet.
Okay.
The way I would say this is I'm doing these by hand right now to understand what needs to be done. Then when we get to, well, now we have, thousands of these, what do we do to do that? And I'm sure that there's a lot of work like the kernel has done, the Linux kernel has done, that could be helpful with that. As long as they tend to venture rather freely into unstable. And I kind of would rather avoid that just for usability.
And I guess, yeah, my next question is more broader. I mean, having done all this, to sort of try things out and sort of, do you have some notion, is it worth it, right? Is it worth
Very
the
much
complexity to do all this? Yeah.
Very much so. At this point, working on my keyboard firmware is quite pleasurable. It feels like I'm doing Rust development. It feels like I'm doing Zephyr development. It's like the best of both worlds seem to come together. The edges are really messy still, and when I have to do something new, I end up spending a day writing a whole bunch of code to go do that. But when I'm off working, I do my development in Zephyr, and I'm getting the stop notification. When I do my development in the keyboard firmware, I have this crate over here, and it runs on the host. It has unit tests. I do cargo test in that directory. I make everything work. And then it gets pulled in with no standard into my application, and it just works because it's been tested and all that stuff. So, there's definitely a lot of that. I think that's all the time we can keep talking out there if we need to. Thank you.
Hello, hello. I don't. Can you hear me?
Yeah.
But I don't know if it's.
I don't know if it's on yet. Yeah, it is.
Yeah, it's.
Probably to move it.
It's.
And then on the other side.
Can you hear me? Okay.
Yep.
Yeah, I don't know if the online guys could do that. Let's wait just to the. Okay. Just to the. We're about to start. Hi everyone, Rodrigo again. I'm here to talk about the new features and roadmap of Zebus since the last session I did on Prague last year, right? And I'm going to start with why Zebus, right? We started Zebus in the past because one-to-one communication is easy, right? We have a lot of kernel objects or tools that enables us to make that kind of thing. But when we start thinking in a more complex way, for example, one-to-many, we don't have so much options. And for example, here we just have mailbox, and you need to do a lot of manual things there to make that work. So it's not easy to do that. And even if you think in a many-to-many communication topology, it's really hard to do. Even if you are thinking a two-way communication, for example, here we would have a lot of queues or FIFOs or something, right? It's not easy to do. So we brought the bus here. The bus enables us to make the threads talk each other in one-to-one, one-to-many, and many-to-many ways, right? And this is the current status of Zebus. right? We have two kind of subscribers and one kind of listener. We have two kind of subscribers and the listeners, and now we can publish two channels through EOSS, right? Which is a new good thing. And one of the advantage of use Zebus is the decoupling. When we have communications, we have a coupling between from the producer to the consumer. In this case, we can think in three more general couplings. Space, when the producer needs to know the consumer, the time when they need to work at the same time to make the communication work, and the synchronization, which means that the consumer cannot do anything other than wait for the communication or act during the communication, right? With Zebus, mainly for the subscribers, we have total decoupling. They don't, the producer doesn't need to know the subscribers. They don't need, it's not necessary to have the same, the communication at the same time, and then the subscribers can do a lot of different kind of things. They don't need to wait the communication to act, okay? For listeners, as we need speed and we need to be more fast, in fact, we have just because space decoupling is one of the most important ones, because the consumer, the listener, doesn't need to be known by the producer, but the listeners cannot just run during the publication process, and they cannot process other workload than the communication, right? So they are fast, but they have some limitations about that kind of thing, but it's a trade-off. You need to pick up what you want. So the contribution statistics from Zebus, I took some, I did a query there, and since last year, June, we had 28 pull requests. We have 3 from the community, other community members, and 25 from myself. And thank you the community for contributing and help. I would like to see more people involved on that, please. We have a lot of things to do, and I am only in Portuguese I say eu keep. It's my I only keep team. I don't know. And for that, going on, we have 3 core features during this year. We have 3 core features that are interesting to tell you, okay? And other improvements, documentations. I did refactor the benchmark sample, which is a really big one, and you can do a lot of things there. I improved some C++ compatibility and fixed some small minor issues and things like that, okay? But we are going deep on that 3 core features. So beginning with the observer storage, at the beginning, for example, here we have 2 subscribers and 2 listeners, and for that during the channel definition, we would have a kind of list with a new ending list or array of observers. And if you take the channel struct as a row on a table, we would have this kind of thing here. We have one value for each column, but for observer, we would have a list, which is not a good way to organize data. And taking some database or good practice, normal forms and things like that, I separated them in a different table or struct. So now we have just the channel definition, and we have an object or a relationship called observation right now. The observation is just a reference to the channel and to the observer. And now we have an additional enable flag that enables us to make that enable or disable individually, which is good, and it gives us a lot of flexibilities. And the best part of it is that we can define observers, static observers, in in separated files, in different files. Before we could just have static observers during the definition time. So all the observers here would be static, and they were part of that array there. But now we can use the Zebus channel add observer to add that relation in a separated file. So here we are decoupling or making the space coupling less coupled, in fact, with the channel. We are not talking about consumer producers, but we are talking about channel observers. Now we can add observers without intervenience of the channel, so which is good for modularity and other things that make your code more separated, right? So we can have that kind of thing, and to make sure that the sequence of the delivery notification sequence was kept, I added a priority sequence number here, which tells a VDD, the virtual distributed event dispatcher, how to notify the observers, right? So here we have, for example, the VDD will notify first L1, then S1, and then L2, and then S2, right? Because the numbers. We are increasing it. It's not a priority manner in the opposite sign, right? We are using that in that direction. In this case here, if we use 3 for both of the observations, we could have the same result because we are using lexical order additionally to the number. Okay, so it's just a tip, but now we can define static observers spread out. It's good. And you cannot, it's not necessary to rely on runtime observers using, I don't know, heap and things like that, okay? For whom that are trying to use Misra C or something, this is a really good thing to do. And another benefit for it is before we just have the enablement on the observer, right? And now we can disable observations individually. So you can even disable the subscriber at all, as a whole, or you can disable just one observation. It can be static or runtime or runtime observer. Both can be disabled on the fly, in runtime, right? So you can do that in a more granular way, which is good because you can keep your subscriber enabled and just disable some channels which you don't want to receive notifications at that time. So for that, we have, in summary, we have static observers in separated files, individual masks, right, which is good, and a sequence priority to make the notification sequence as we want, okay? Master subscribers. The master subscribers were requested since the beginning, and I was trying I was reluctant to add them, but I tried to find the best way to add them to Zebus. And in fact, the master subscribers are subscribers that receive a copy of the message. Before, we just have listeners and subscribers, right? The listeners were executed by the VDD, and during that execution, they could access directly the message without needing copy or something like that. They could access directly the message, which is good. And the subscriber only receives the notification of a changed channel, not the message, in fact. They should get to the channel and retrieve the message to consume the message, in fact. A lot of people don't understand the meaning of them, but they are really complementary to the listeners. And now we have master subscribers. They receive a copy of the message. Okay, so during the VDD execution, the VDD will distribute some copy of the message to the master subscribers. Right, so you have listeners for fast subscribers for, let's say, soft notification, and message subscribers to hard notification with the message at all. So we done that. We rely on NetBuffer. NetBuffer is a really powerful tool. I would change the name from NetBuffer to Buffer to be more, I don't know. It's weird. I am using NetBuffer on Zebus. It's not Net, but it's really interesting. And I showed that here just to mention that we use a pool of NetBuffers, and the message subscribers has they have FIFOs, right? So we can put some NetBuffers on the FIFO, and then they can consume the messages. So the NetBuffer works with a kind of reference count. So we can locate message on the heap and make them to take care of it. It's really interesting because we don't need to allocate that manually. So the process is we use a NetBuffer, we copy the message to the heap to keep the stage of the message, because during the publication or after that, you can change the message, and that message, the first message, should arrive on the message subscriber. And we do that for the three of them here, right? And then we send a reference of the NetBuffer to them. And when they receive the reference, they know where is the message. So they make a copy, they unwrap the NetBuffer, and the NetBuffer remove the reference to the heap allocated, right? And put the NetBuffer on the available pool again. And you do that for all the message subscribers. But the latest one, when we don't have any more references to it, the NetBuffer will delete the heap memory. So the user doesn't need to know that, they just receive the message on the message subscriber. This is a kind of under the hood way to work, and I'm going to show you. I was trying to be transparent or something. But also, on that case, we have a copy of the message on all the message subscribers, okay? Some tips about message subscribers. We can also use static allocation for it. If you want to avoid a heap, you can do that, but you must make sure that the message size that you are configuring there will enough to fit all the messages you are exchanging on that message subscribers. There is an assertion there that helps you if you enable asserts there and you don't have enough room to fit the message. The assertion error will raise some problem and tell you must use at least 20 bytes for that, for example. You must take care of the pool. We have just one pool for all the message subscribers and channels. So it's really a global big pool, and you need to take care of that and make sure that you have enough a big enough pool to make your system communication to work without a lot of failing, right? And another tip here, we now have a different sub weight, right? We have Zebus subscriber weight message. In that case, we receive the channel, but also the message. And if you are observing two different channels, you must be sure that this message is big enough to hold any of those. So using a unit like this would be really easy and straightforward. It's not necessary to define manually the size of it, right? I usually use that like this. So the latest one, and one of the most important, is the highest local priority protocol. With the advent of message subscribers, we could face a lot of prioritization problems, right? And if we take a look at that scenario here, we have one subscriber, 2 listeners, and 2 message subscribers, and 1 thread publishing to the channel. Following that sequence here, and that priority configure here, we could see this kind of thing. If T1 tries to publish to channel A, we would have a channel log, right? A copy of the message, and the listener one execution, that what's good. But when we send a message, a copy of the message to MS1, the MS1 has more priority than T1, so it preempts T1, which is not good at all. And MS1 runs and then T1 get back to the MCU and sends a copy of the message to MS2, again preempted, and then it will send a notification to S1, run listener 2, and then after that unlock the channel, and so S1 will read the channel and get the message. We have 3 problems here. We have a priority inversion, because S1, the highest priority thread, is the latest one to consume the message, which is not good. And we have two preemptions, and we have a listener running after the observers, which is not good at all, right? So to solve that, we implemented a highest lock. So before we used mutex to that, but the priority inheritance was not helping in that case because MS1 and MS2 are not part of the mutex intended queue, right? So they are out of that. So the priority inheritance of mutex is not working, was not working for that scenario. So I removed mutexes and replaced that with Semaphores and implement a highest local priority protocol. Is an elevation algorithm, priority elevation algorithm that do things like that. We have a critical resource, and for that critical resource, we have a ceiling priority value. It's not a priority ceiling, right? It's slightly different, because the value is defined by all those tasks that may request, not is requesting at that moment, right? So if we change critical for channel and task for observers, we can see that the channel would have a ceiling priority with the highest observer priority. So you could avoid a lot of those problems I talked to you. So to define that, we have, for example, here we have S1 as MS2 and MS1. MS1 has the highest priority here, so the ceiling priority of the channel would be 1. So with that priority, T1 could publish to channel A without priority inversions, without inversions, without preemptions, and no listeners after observers, right? And sometimes the S1 can be disabled or abort, the thread is abort or something. The channel can be, the channel ceiling, priority ceiling can be calculated again. And in this case, we have, for example, 3, and the channel will receive 1. And that scenario becomes this one, which is when T1 tries to publish to the channel, the VDD will elevate the T1's priority to a highest priority than S1, and everything goes really smooth, right? We don't have priority inversions, preemptions, or anything, right? And after that, the highest priority thread will consume the data, will consume the message. So S1 is the first one to touch it, and then MS2, and then MS1. Okay. So we have the HLP requires a priority for the observers, and until now we didn't have this kind of thing. But to do this kind of calculation, we need to attach the subscriber to a thread. So usually we just use a subscriber on one single thread. So we need to attach. We have the detach method function as well, but we need to attach the subscriber to a thread to make sure that the thread's priority is inherited by the observer. Okay. So in summary, we have short VDD execution. We have no priority inversions. The listeners are always executed, are usually executed before the subscribers, which is the intention of it. And if you design the system to avoid inversions, you would not see a lot of overhead because you would not have elevations, which is good, right? But if you don't want to have the HLP work on your code, you can disable that. It's a configuration that you can disable that. And you can use plain semaphores. But you must be aware that you face some priority inversions, preemptions, and so forth, okay? And a good thing here that several people talked to me about that and asked that before. Now we can publish to channels, Zebus channels from ISRs, which is good. But we need to make sure that the listeners on that channel are not so long or heavy because you would increase the ISR latency, right? So make sure that, or avoid listeners, or maybe you just use subscribers on that kind of channel. For example, you press a button, the button will publish to some channel. Maybe it's good to have just subscribers there because you'd have a callback calling another callback and so forth, which is not good. And a little about future. One of the things that I'm trying to do is to isolate some pool for a critical part of the system. For example, you have a portion of threads that talk each other, that are more critical than other part of the system. And you want to be sure that always you have a net buffer on the pool for that communication. So we can separate that. It's not implemented yet, but I think that would be there soon. And you can create a heap pool or a stack pool and put that separated. And you can share the same pool with some channels. Would be good to make that more safe or more critical adjusted. Okay. Another thing that I'm working, I'm helping the IoT applications from a team from Nordic to implement the multicore Zebus, which is a really big challenge. This one is when you have multicore, you'd have a channel on both cores, and you need to keep the state of that consistent, right? Which is not so easy because the other core can be sleeping, or you can have some RP message problem and everything else, okay? And for making that easier, we have two new things added to Zebus. We have the notion, the concept of shadow channel. The shadow channel is, for example, here the payload one is a kind of channel that it's a read-only channel. You can only this core here just can read or receive some notification from the channel, but in this core we cannot publish to that channel. But on this core we can publish on the actual channel, and all the things that happen to that channel will be reflected to the shadow channel. And we have an proxy agent in the middle, right? They know how to talk each other to make that consistency happen. And if we take a look at that and change the medium here, we are talking about multicore, right? But if we change that for two MCUs talking through, for example, UART, you could have multi-target, right? You just need to change the medium here, the agent talk. They know how to talk, but you just need to change the medium, and you can have you could have from multicore to multi-target, which is really good. When you are thinking on, for example, embedded and host, you could have a Zebus on the host talking to a Zebus on the embedded device through a UART, for example, which is really good for simulation, for testing, and so forth. Okay. And the latest topic is what I'm calling Zephyr daemons, right? This is a kind of, I don't know, it's a really long road, but I could see a lot of things, and I think that it's almost time to have daemons on Zephyr, right? And I don't know if everybody, I believe that everybody's know, but a daemon is a service that is running on the background to help other processes to work, in fact, right? So why doing this? We could do that using a common API, command response event, right? And with that, we would have a core for the daemon and an adapter. The adapter could be exchanged to talk to the driver. So we would have a daemon that we could change the adapter to make that more flexible, and we would have a piece of the application running properly, and we can access that like a microservice. But it's not a microservice because it's a thread. But we talk that, we can call that a daemon, right? Because it's not outside, it's inside, and it's running to help us. And for example, we could have this kind of scenario where we could have a daemon for MQTT, a kind of DB, or buttons, simple things that we still are programming these kind of things. We still need to do code for buttons, for example, and other things like, for example, MQTT. If you take a look at the publisher sample, you'd have 500 lines, which is not, whoa, 500 lines for a sample to publish something on MQTT is too much, right? It would be easier, because if you go to the desktop, for example, you have Mosquito, pub, and you can do some I don't know, some arguments there, and okay, that's running. So on Zephyr, we have to do a lot of work and redo that every time. I think that all the companies are doing that, almost the same thing, repeatedly. So I guess we can, it's not for everything, but we can find some parts of the code that we can put inside a kind of capsule and make that reusable for everybody. It's almost like that. And it would be like this one. We could have a kind of configuration. We publish to a command channel, and we try to check that on a response channel. And we could publish that just use a kind of struct and publish to the same command channel, right? So the command would be kind of union with some metadata, and it would work. In fact, we were switching from 500 lines to some configurations and I don't know, a couple of lines, right? It's powerful, but it's limited. But for the majority of the usage, it's the enough thing, right? I don't know how many companies are tweaking a lot about, I don't know, MQTT or common things, and maybe this is part of it. Okay, so and I was planning to make the communication interfaces mapped on a kind of interface definition language, I don't know, ZCBOR, CDDL or something, a protobuffer, to make that available to other languages as well. For example, we see people talking about using Rust, Python, and Ray, I don't know how to say that. It's a Rust virtual machine that can run there. And if we have a lot of daemons defined internally, all the C part, all the driver part, the hard thing, the hard parts, that's already done on Zephyr would be encapsulated on a really well-defined API with a protobuffer, and the other side just need to access that part. So, for example, an application in Rust would not be necessary to have, for example, syscalls or a lot of detailed things there, because you just need to use a Zebus well-defined API, and you could have just a wrapper on the Zebus and other small things on the system to make that work. So I think that it would help us to make a more, let's say, a more prepared for virtual machines or something like that. Okay. So for wrap up everything, we have three new features. The observer storage, right? We could do a lot of good things with that. A new kind of subscriber, and a new priority elevation protocol, which took 90 days to get merged. A lot of things to be done at that time. And for now, we have the individual pools to make that. It's a small feature, not so hard to do. Zebus multicore, which is a big deal, and daemons, it's a big deal. But it's a start, okay? And I'll open for questions and okay.
Thank you for the talk. Zebus is new to me, so, and I find that all.
Yeah, it's working, I guess. Yeah.
Sucks. I'll try to. Testing? Okay, that's better.
Oh, that's good.
A
That's
little
better.
bit. My question's around the VDED and why that runs from the publishing thread context, and if your idea of daemons could be applied to that to maybe move it outside that publishing thread context to get around some of the limitations on the listeners needing to use that stack and context.
Okay, great question. At first, we had a centralized event dispatcher. In fact, I call that virtual because it doesn't exist. In fact, because it's just a function call on the publisher context. But it was to avoid priority inversions. In fact, because if you have a central entity publishing something, what is the proper priority for that? Because if you have a really, I don't know, low priority thread publishing to something that just low priority threads are involved, you are using a high priority thread to make that. So you are avoid to, I don't know, highest priority thread to work because you're publishing something. So in that way, you could have more different kind of context, talk context, without interfering each other. High priority threads talking to each other without interfering in the low priority threads, and the scalability of that is really huge, right? Is okay? Okay. Any other questions? Oh.
Hi, Rodrigo. Thanks for the presentation. I have a question around the channel definition. When you're defining a channel, do you need to know at that time what are the number of observers and what are their types, or is that somewhat abstracted?
It's separated. It's a kind of when we define a channel, we have a kind of array defined, but in the implementation we have separated object creations in a kind of list, but it's not on a single list. We are iterable sections for that, right? We have iterable sections, and we can link them one by one, and it's really easy to follow.
One of the things that we'd be interested in having is the ability for the publisher to know how many subscribers it has so that it could potentially shut down and stop publishing if there are no subscribers. So for a more dynamic context, say you've got accelerometer data and you've got a task that's, multiple tasks that suddenly, have been scheduled to stop. So therefore, you want the device to go into a lower power mode and turn the accelerometer or stop the accelerometer data from continuing to publish that or even sample. What would you recommend as a mechanism for the publisher to be able to know how many sort of dynamic subscribers there are?
You need to know how many subscribers, the publisher would need to know how many subscribers it will affect.
Well, essentially like maybe an event or something like that to be able to notify that you know, the number of subscribers has changed and that number is now 0.
Yeah, the principle is to make that detached, right? It would be not necessary, in fact. But you can use, for example, user data pointer to add some metadata to the channel. It's possible. And you can, for example, make some atomic there, and where you have some observer, you can increment that count. And when you are not enabled, you can decrement that count. And you have also a validator function, which is run before the publication. So if you could have a kind of validation that tries to find out how many observers that function has. If 0, the validator would return false and the publication would not work, for example. It's a way to go, but it will cause error, but you would not publish if you don't have any observers, right?
Okay. Yep.
Make sense? We can chat more if you
I have to think about it a little bit more whether that could be used to actually shut it down and then
Are
dynamically start it again. Yeah.
Okay, we can. Another there.
For multicore, how does the proxy differ to the daemon store you make, or is your proxy a daemon?
Oh, yes, maybe they are the first daemon, right? And I don't know. They are a separated thread that need to work in parallel with all the system, but they're individual and they need to know other agents on the other cores. They need to talk to discover something, and they need to have some information about the channels, the shadow channels and something like that. And for example, when one core wakes up, the agent of that core should ask the other agents, oh, I have 2 shadows here. I don't know, did you change those shadows? Yes or not? You could keep the consistency on that part. But yeah, the daemons are a long journey. It's not for the 3.6 or 2.7, maybe 4. I don't know. We need to discuss a lot more about that.
Okay, thanks.
Does anybody? Okay. Okay, in time. Thank you.
Okay, are we, looks like we're at 11 o'clock and this is working. All right, anyway, hi all. Excuse me. Yeah, my name is Andy Ross. I'm a software engineer at Google. I've been working on Zephyr for a good while now. I think it's actually close to 8 years. Actually, maybe slightly more now. Sort of all over the bottom layers of stuff, mostly in the kernel, SMP, that sort of thing. But what we're here talking about today is kind of the intermediate layer, the glue that lives between my world and the app layer, and that's interprocess communication. It's something that's been historically pretty varied within Zephyr. You know, we've got a lot of choices. We've got a lot of stuff going on. And it's a real common problem is that people come to places like Discord and have questions about, you know, what goes where and what's supposed to work and what is this tool for. And I thought it was probably time for a kind of quick discussion about kind of like where we are and where, you know, I think maybe we want to be and what we want to be pushing people towards. Needless to say, Zephyr has a lot of tools in the box. It's a mature system. Mature systems are great. You know, we've been doing this for a long time. We're real confident about the system. We've shipped a lot of products. It also means we've kind of veered down some, you know, interesting cul-de-sacs along the way, and so there's some, you know, archaeological evidence of those eras that we'd like to have some, you know, documentation of. That leads to a bunch of developer choice. That, you know, you've got a lot of things you can pick. Too much choice, especially too much choice, you know, without a lot of guidelines in new apps and new markets, tends to lead to bad decisions, missed opportunities, you know, things that you might have done better. And it's important to recognize that Zephyr is it's still a real-time operating system. We're still in RTOS. We still care about small systems. I mean, our roots are in really tiny systems, you know, like 4K RAM kind of things. And we tend not to play in that sandbox much anymore. But we're still much smaller than, you know, other systems people are going to be coming from that need to deal with these same problems. I mean, like the biggest systems we've got right now are order of 16 megabytes or so. You know, like the audio DSPs that I tend to work with, most of them are quite a bit smaller. People need to worry about code size in Zephyr, and having lots of choice and lots of things you can link in and lots of stuff you can use tends to lead to larger binaries that nobody really wants. So the sort of basic, you know, audience for the talk, you know, who's supposed to be here? I did promise this was going to be intermediate level. You know, we're not going to talk about assembly language. We're not going to talk about architecture layer. We're certainly not going to talk about hardware. This is all C code, hopefully. Try to hold me to that. You know, so it's, you know, people who are like, you know, familiar with Zephyr and, you know, really want to see like, you know, deep dive into, you know, the weird stuff that they've seen or maybe noticed or wondered about. You know, people from other systems, like any Linux folks wandering in here who are just curious, might like a tour of how you know, smaller systems, different systems might do the same stuff that they're used to seeing. And really just, you know, anybody who might be curious about concurrent programming in general. You know, things that we all like to think we know about, and, you know, pitfalls and traps that we've all made and we've all learned from. You know, it would be good to at least have somewhere in a Zephyr context we can kind of call that stuff out, because I guarantee we all make those mistakes every week. So why is there an IPC layer, right? I mean, IPC is interprocess communication, right? We have IPC because we have threads. Zephyr's got threads all over the place. That's really the core abstraction that we're providing to the users, is that you can take your code from wherever else it is in the world as a nice sequential algorithm and bolt it into your system and just run it, do this and then this and then this and then this and then this, and get to the end and be done. And that's the way that we all like to write code, because it's the way we all understand, except in big modern systems, you know, there's lots and lots of components that need to do all of that. So the natural way to do that is that you do it with a thread. That means the natural way you do it is with a whole bunch of teams running in their own threads or with their own ideas about how it works. And once you've got threads, you've got parallelism. Once you've got parallelism, you need synchronization. You need, you know, ways to get the threads to work with each other so they don't step on each other's feet. And that synchronization is just a hard problem, and we'll talk some about that today. IBC just provides simpler tools than the very low level, oh, here is how you synchronize two threads running in shared memory. It gives you different metaphors that are easier to reason about. That's the fundamental idea here. And in fact, the core metaphor, and this is the closest I'm going to get to actually defining IPC, because I don't think there is a good definition for this stuff. IPC is about wait until, right? It's the idea that you've got a thread, it's going to do something, it's going to continue to do something until the end of time, because that's the way computers work. And you need a way to say, no, stop, you're not ready yet. It's not done. There's nothing in the queue. There's no command ready. The network is silent. You know, something has not happened that you need to wait until. In fact, I got ahead of myself with the why so many threads. I already covered most of this law. But again, it's important to recognize that we have the lots of threads for reasons that may not necessarily be great design, but are unavoidable. We've got big teams. We've got lots of stuff. We've got things from different sources. The core value Zephyr is providing here is that we give you a way to organize all of this stuff, and threads are an important idea there. And so how do you get, you know, now you've got all the threads, you know, what naturally happens here is that people tend to try to bolt stuff together, and if you don't have IPC, you kind of can make things work, and there's a little bit of source sample code here that is kind of showing the sort of thing that I think we've all done, we've all seen. You know, generally it's some variant of polling, right? You've got something that needs to happen, and in here it's, you know, something to do is a predicate, and you're going to call that, and then you're going to call do something. And if you do that in a fast loop, typically what you see happens is nothing happens, because you're the highest priority thread, and you're sitting there in an infinite loop, and so nobody else is going to run. If you're lucky, maybe, you know, something to do is being filled by an ISR somewhere, and so you might actually notice it happen. Then people try to you know, fix it by throwing, oh, let's throw in a yield. You know, like you look at the scheduler docs for Zephyr, and you see that, yield gives other threads a chance to run. You throw that in. You realize that yield only really works for threads at your priority. So you end up then throwing a sleep in. All right, fine, we'll just sleep. It's fine. You have 20 milliseconds. It's not a big deal. We know that that's our budget anyway. It'll work. Excuse me. Then you realize that 20 milliseconds doesn't actually work, because sometimes you're missing one, and you're not really sure why that happens because of aliasing and the timing. So let's do it in 10 milliseconds instead. This is clearly not the way we do things. This is the problem we're trying to solve. But it's important to recognize, too, that this is tempting, and we'll come back to this kind of code later on, because it tends to pop up in places where you don't really expect. Again, giant problem area. Lots of stuff to talk about, so I think it's important to have a slide on the stuff we're not going to talk about. IPC obviously is a big kind of, you know, abstract conceptual idea. It doesn't only come from the kernel. The kernel obviously needs to provide a bunch of tools, but there's a lot of other stuff in the world that is dealing with the same problems. You know, there's lots of framework code in Zephyr, some of which is quite large, some of which comes from other environments, and they've got their own ideas, right? Like, you know, there was just a talk on Zebus, which unfortunately I missed, but I'm going to go watch it later on, which is a rather higher level, you know, RPC, you know, remote procedure call based way to connect stuff together. Looks great. It's probably something to consider. I'm not going to talk about it. The network layer obviously has its own built-in IPC, and some of that is historical. You know, obviously the network code, you know, arrived very, very early on, before a lot of the stuff that we're talking about today was really mature enough. And also the network code is implementing, you know, BSD sockets. There was a pre-existing API to do what you want. That doesn't work very well with a lot of this stuff, unfortunately. It would be good for that to converge at some point in the future, but again, not going to talk about it. And then there are things like, you know, we've got a SIMSYS abstraction layer that provides wrappers around, you know, Semaphores and mutexes and that sort of thing. POSIX we have too, but we will talk about that a little bit. We're not going to talk about frameworks. And then at the very bottom, recognize that this problem is also solved without kernel interaction at all. And we're developing a big stable of good tools out there. You probably want to take a look at the single producer, single consumer, multiple producer, single consumer tools are lockless message passing things that have no kernel interaction at all. They look really great. WinStream is a similar idea for byte streams. I wrote that one. That was actually for cross-host logging from the Intel DSPs, where we cannot send an interrupt to a Python script on the host, so therefore we can't use the base logging. And needless to say, lockless algorithms like totally out of scope. We're not going to be talking about that at all. But do recognize there's a lot of stuff aimed at this same problem area. And then a final caveat is, well, what if we don't actually want all those threads, right? Threads are really expensive. Threads probably the most expensive single data structure you're ever going to deal with in the kernel. Can you get rid of them? And the answer is, yeah, you can. You can totally do it. That's what a work queue is, right? We have a system work queue that's kind of provided by default. It does exactly what it says. You give it a callback, it'll call that callback in the order in which they were inserted into the queue. It's got some other features too. It'll take a delay for each work item. Work queues are simple, they're straightforward. They're used by a lot of subsystem codes, so they're fairly cheap. That is to say, you're probably linking in the system work queue already, and if you are, you don't take any extra code size to use it. And because they're in order and one at a time kind of things, there's no decision needed on until that we were talking about earlier, right? That's, you don't have a thread, so you don't need to wait. You just got to do everything you've got. And this is async code, right? I mean, like this is all the rage out there in the rest of the world. More elaborate environments out there, starting with JavaScript about 15 years ago, and now like Python and Rust are into this kind of thing too. Have big, elaborate, syntax-based frameworks around that. Unfortunately, we don't. Work queues, you're going to pass it a callback. It's a C function pointer with a closure where there's the void star argument. So we don't have the level of glitz that these other environments do. But as a synchronization problem, it's appropriate, and it's appropriate for exactly the same reason. So do consider it. But again, that's not really what we're talking about today. And then the final point there is just to point out that there is a work queue just does everything in order, right? So all of the RTOS features that you're used to about controlling latency and priority and all of that stuff have nothing to do with work queue items. The very last point is there is actually a P4 work queue in there, totally out of scope for this talk. I wrote that a couple years ago, which basically turns the work queue items or work queue-like items into little threadlets. They've got their own priorities and can preempt each other. It's good to look at. Go take a look. So how does this actually work? All right, so we've got a problem, and we've got to have a solution in the kernel. The kernel provides the IPC layers as the top layer. It's got to have something to do on the bottom. And the first thing, of course, you need for any kind of parallel environment, and everybody learns this in school, is mutual exclusion. You have to have the idea that you're going to be looking at some data. What that data is not really the problem of the framework. You're going to need to look at it, and you're going to need to say, hey, I know for sure that the picture that I'm seeing right now and the values that I'm computing are not being seen in a different state by somebody else somewhere else that's going to make a different decision. So you do that with a lock, right? And everybody's seen that, right? You do some level of locking. We've got actually a bewildering variety of locks at the bottom level of the kernel. We've got sched locks and all of that stuff. But at the very bottom layer, this is always done with a spin lock in Zephyr. And a spin lock is well, actually, on a single CPU system, a spin lock is nothing. It just masks interrupts and goes on. On an SMP system, it's got more work to do. So it's got there's a single bit of information telling whether it's locked, and it'll sit there and spin on that until it's available, and then atomically take it and move on. The spin lock is not the API we're talking about right now, but it's important to recognize that that is the API on which all of this is based. There was a great discussion about ticket spin locks yesterday, if folks saw that talk. So this is, it's evolving as we move on, and it's the kernel's basic idea. But it's not a great choice for apps, right? And why is it not a good choice for apps, right? It's well, the big one is it doesn't work in user space, right? It has to mask interrupts as just a native abstraction that it's dealing with. Since it can't mask interrupts in user space, you can't use it in user space. We'll talk about it. There's a POSIX one later on. We'll talk about it a little bit. If you're not careful about it, obviously you've masked interrupts. You're going to cause latency problems. You're going to block out interrupts. In the kernel, where we kind of mostly trust ourselves, sometimes sort of, we take that as just a design point and make sure that our critical sections are small. That's a real heavy burden to use with apps, especially when you're calling into things like third-party code that may not be as careful. So not a great choice for apps. So we'll come back to that in just a moment. Second basic building block, and this is the sort of more important one from the kernel's perspective, is blocking inside of Zephyr. If folks are familiar with the kernel code, we actually use pend as the verb and not blocking. I'm going with the Unix term here because I think people are going to be more familiar with it. The thread can't be running all the time, right? Like computers will run in perpetuity forever. You need to let other threads run. You need to stop them. So the kernel has the ability to stop a thread, right? You context switch out of the thread, you take the thread pointer, and you stick it into a list. And we call that list await queue. And that's really all it is. It's just an ordered list of threads. There's a little more complexity in that we sort it by priority order. So when when you wake up somebody who's waiting on it, it wakes up the highest priority one. There's a little bit of fanciness to the back end. We can store that as just a simple, doubly linked list in order, or we can store it in like an RB tree if you want to have like 100 or 1,000 threads waiting. If you have the memory budget for 1,000 threads, we can do that algorithmically fast. And really, that's all about there is to say about the data structure. And then behaviorally, it's works like you expect. You pop it off the list, stick it into the list, it'll sort it into the list. The only gotcha though is that it must be called when holding a spin lock, and it will release that spin lock atomically with the placement of your thread into the list, and that's to eliminate what is a fundamental race condition we'll talk about in just a bit. And it also takes a timeout parameter. And this does exactly what you think. It's like you're going to go to sleep, but you want to wake up after some amount of time. You can pass K forever if you want to sleep forever. You can pass K no wait, which means return instantly even if you aren't going to do whatever it was you wanted to do. This is a way to represent like non-blocking I/O and that sort of thing, which in Unix typically is a little more complicated or a little more API specific. In Zephyr, it's just one parameter to one utility, and then it gets percolated up. Basically, everything in Zephyr you're ever going to do that's going to block, it's going to take one of these parameters, and you can specify whichever timeout you want. The other good thing about K-no-wait, I should mention, is that it allows you to work in an ISR context. It's a natural way to say, hey, do something like insert into a pipe that might be full, or down a semaphore that might be empty, that sort of thing, and then return instantly with an indication that the failure happened instead of having to block, because needless to say in an ISR, you can't block, you're not a thread. And again, the final point, just pointing out that other operating systems have this kind of thing, but it's a little bit kludgy, right? Unix select and poll allow you to do this on arbitrary file descriptors. Read and write don't have that idea. Sockets have timeouts that you need to specify as options at the network stack layer. We put it all in one place. I think it's one of the nice thing we do. So now let's finally talk about an application visible IPC primitive. That is KSEM. Most people are familiar with semaphores. You learn about them in school. I'm just going to zoom really super quickly through. A semaphore is an abstraction of the idea of a queue. Something is going to happen, right? You're going to take I call it a token here. You're going to stuff a token into the semaphore. The semaphore is going to say, okay, great. Well, is anybody waiting on a token? I've got three threads that are blocked here. It's going to pull the highest priority one off, run it. If somebody comes in with another token, or another, or a third, or a fourth, it'll just keep counting up, so that if 4 threads come by and you've got 5 tokens available, they'll all get to run. And if 7 threads come by and you've got 4 tokens available, 4 of them get to run, and then 3 of them block. So it's kind of like a queue. Each token that goes through is one person that gets to wake up. And again, I'm using different terminology here, but you notice that the read kind of encapsulates that wait until idea I mentioned with IPC, right? You go to the semaphore, you down your semaphore, which is the term I'm using here. Zephyr calls it take, and you will block. If there's nothing available, you're going to stop. Again, historically, the naming, as I mentioned, is kind of awful. The original semaphores were defined by, I want to say it's Dijkstra, is that right? But it was V and P were the original operations. Up and down is more common. That's what you see in the Linux kernel. Post and wait. I don't know that I've ever seen that anywhere else, but it is in fact the System 5 semaphore API. Zephyr uses give and take, which again I think is unique to Zephyr. I don't think anybody else does that. Doesn't really matter. Most of those are fairly clear. You see some sample code here. You'll see this again and again and again throughout every subsystem in the Zephyr tree. It's really pretty straightforward. There's an error code obviously for ksem take, because that's a blocking operation. There is no such error code for ksem give, because that is not a blocking operation in the semaphore. We're going to talk about that in just a second. Use semaphores everywhere you want to. They are fast, they are small, they are fair, and I'm putting that in scare quotes because there's a digression here that is scheduler specific but not really IPC specific. When you do something in Zephyr almost everywhere that is going to change the scheduler parameters, change the idea of who's going to be most runnable right now. Like for example, you give a semaphore and somebody higher priority was waiting on it. Zephyr is going to do a synchronous reschedule. That is not universally true everywhere. There are exceptions, but semaphores are not one. Semaphores are what are called a fair semaphore. That's not always what you want. Occasionally there are performance benefits to waking somebody higher priority up, but then finishing your task for cache residency reasons, or because you're about to wake up somebody even higher priority. before going on. But that is the way that the KSM works. And the big one is it's already there. Like, I mean, there are semaphores within the kernel. There's semaphores in almost every subsystem. The incremental linkage cost of using a semaphore in your own code is basically zero. Use a semaphore. If it's appropriate to your problem, you know, don't pause. Don't worry about what the best choice is. Use a semaphore, and it includes on things that aren't necessarily semaphore-related problems. You see this pattern pervasively in Zephyr, right? You take a semaphore, you set its count to 1, you initialize it to 1. There's some sample code there that shows you how to do that. Or you could just, you know, do a ksem give right after you initialize it. And then ksem take, you know, decrements the count from 1 to 0. That is a non-blocking operation. You're going to return instantly. The second person tries to ksem take, and they're going to block. Then you ksem give, and that wakes them up, and they get to run. That now has become a lock, right? It's one-to-one analogous with any mutex API you're ever going to see, and it's based on semaphores, so it's incredibly lightweight. And Zephyr uses this everywhere. I think this is a great pattern. Again, it has that benefit that because semaphores are already used everywhere, there's zero overhead. It's super fast. Ksem take in the uncontended case where there's already a count in there is dozen cycle kind of thing. It's, you know, it's really very, very fast, maybe 20 cycles. It depends on your hardware, right? But all it needs to do is, you know, go to a single address of memory and decrement it, and there's a spin lock around it. So, you know, like 2 interrupt mask operations, and you're decrement and you're done. It's really only slightly slower than a spin lock, and in fact, on SMP platforms, because of this, if it's a contended spin lock, there's a relaxation step we need to do that can actually be getting, like, with Intel ADSP is now up to, like, you know, hundreds of cycles of relaxation required. So in fact, semaphores may even be faster on some systems. So use this. Like, if you know, again, if you need a lock around something and you're not in a level of code sophistication, like not developer sophistication, but there are just some places you don't want to use a spin lock, right? If you can use a spin lock, use a spin lock. Spin locks work basically everywhere. But if you're in user space, or if you're in library code that's going to need to call into some arbitrary thing that's going to need to do a lot of stuff, and you need to have a blocking lock, this is the one you should be looking at first. We do, however, have a dedicated mutex primitive. Kmutex is there. It does work. It's good. It does everything that the spin lock that I just mentioned does, plus better error checking because it can detect the misuse problem. What if you give the lock more than once? You can end up with a lock that has a count of 2, and now you can have 2 people hold the lock, and that's really bad. It also provides priority inheritance, which is a really cool RTOS feature where the circumstance where you're going to need this, right, is you've got here, okay, somebody goes and takes a lock, right? Low priority thread takes the lock. A higher priority thread comes in and preempts the low priority thread and starts doing stuff instead. Now the low priority thread isn't doing anything. A higher priority thread comes along and needs to block on that same lock. It won't get it because the lowest priority thread has it already and won't run because there's a medium priority thread that's already blocking it. So you need to bounce down 2 layers to give the lockup to get back up to this one. But that won't happen because, in fact, the middle layer is going to run instead. Ergo, it would be kind of nice if you could grant your priority to the owner of the lock so they can get their stuff done really fast. It's a good feature. It's not that good a feature. It results in a larger, slower, bigger. Again, this is not used by the rest of the subsystem, so you're going to be paying linkage cost to use it. Larger, slower, bigger abstraction. And the truth is, PI is really only useful if all the blocking in your system is done on a Kmutex. If your high priority thread is blocking on a semaphore, if it's blocking on a pipe, if it's doing some other I/O that's going to enter a wait queue in the kernel, you don't win for this. So it's harmless. It works fine. Certainly don't refuse to use this. But again, within Zephyr, the overwhelming pattern is to prefer ksem for this application. And you might ask, why don't we have an abstraction around ksem to do that? I don't have an answer for that. We probably should. So now we're moving on to the rest of the stable here, where things start to look like a lot more overlapping. So the idea is that we've got this wait until operation, right? We're going to wait until something is ready for the semaphore. Wait until someone has called ksem give. So the semaphores do that part on they do that blocking on the read part, right? The wait until. But what if you got data, right? You're going to stuff some data into a pipe message queue, something like that. Well, that might be full, right? So you actually need to be able to wait until there is space in the queue too. So there's a little bit more work here, but it's the same basic metaphor, and it works really well. And there's a quick digression here where I'm showing a, a little command line down there at the bottom, pointing out that, like Unix obviously has been using file descriptors since the beginning of time. As like the universal process interop abstraction. And so down there we've got, a little command line. I think folks probably recognize what that does, right? This is going to tell you who's given the most commits to a Git archive. But think about what it's doing. It's 5, right? 1, 2, 3, 4, 5 different processes. They're all like separately launched, separately spawned, doing their own thing with different code, in some cases to APIs that were specified decades apart. And in fact, they're on modern systems like this 12-core, monster mid-range Chromebook. They're all running on a physically separate CPU. And yet they're talking all via just exactly one abstraction. There's only one piece of information. You need to know how to get all these guys to talk to each other. And that's, of course, the Unix pipe right there. So, I mean, queuing is great. Use queuing. We've got a lot of queues. So we've got like 9. Well, it's not that bad, but it's pretty bad. So I'm going to go very quickly through some of them just to give folks an overview. K50 is the first one you're probably going to see. This was a very, very early one in Zephyr. A lot of the sample code likes K50. It's a great choice for space constrained systems because all it is queuing up is just app managed structs, right? I mean, you've got some memory. In that memory, you need a void star, to have a singly linked list node. And that's really all you need to do. So the kernel doesn't need to do any allocation. It doesn't need to do any space management. There's no buffer to fill up. In fact, which makes a little bit of a lie that you need to have the blocking on write. There is no blocking on write on K50. And it works great. And you can see the sample code here. As a digression, I will note that I'm a little bit contra-idiomatic here. K50 is a intrusive data structure. The way we defined it and the way our sample code works, it typically says you must put the list node at the top of the struct that you're going to insert. So in this case, the myrec struct would have the Q node up at the top. Therefore, you could use the pointer to the myrec directly in the K50 get and K50 put. That's not the way that intrusive data structures work in most of the rest of the world. It's certainly not the way they work in Linux. It's not the way the slist and dlist and rb-tree APIs work in Zephyr. So here I'm kind of like, I'm using the container of macro to give it a Q node, even though you'll see it's a void star there. We don't have a KQ node T struct type. We should, we don't. It's an API wart. So I'm kind of inventing the abstraction here just by calling it a void star. And this is pretty much exactly what you want. If you just want a linked list of stuff and then have synchronization around it to block when it's empty, use this. Queues are great. Queues are very simple. Once you're over the hump of the intrusive data structure stuff, there's not much more you really need to worry about. So use that. It's also worth pointing out that KQ exists in a couple of variants. It's a singly linked list. You can insert it either the tail or the front of the list because you need both pointers in order to do your list stuff. Therefore, we've got a LIFO that is also implemented in terms of the same abstraction, which is basically conceptually a stack. You put stuff in, and it grows bigger, and you pop stuff off the top. But there's linked lists in both cases, and they use exactly the same code. We do have others. There is a message queue abstraction. Unlike the one we were just talking about, this one is not intrusive. You're using fixed size messages. It copies them into a buffer, copies them out of the buffer at the reader level. There's not a whole lot more to say. It does exactly what you expect. Where I was mentioning earlier that you do this blocking on write problem, this does provide that. If you try to write into a full message queue, that's exactly what you're going to get. It's simple, it's reasonable. If it fits your problem, use it. They do need to be fixed sizes, so there's a little bit of extra work. Obviously, the copying of the buffer is extra work. The buffer itself is extra memory to worry about. But in a lot of cases, you do have more dynamic storage management, and the linked list of structs is not as useful. When we get to user space, it's also something the copying works as advertised, so it's it doesn't have the weird behavior that FIFOs have in user space. We'll talk about that in a bit. Pipes, even more of the same, basically. Pipes are now an ordered stream of bytes. In fact, pipes are more or less one-to-one with a Unix pipe. They do exactly what you want them to do. Both message queue and pipes, I should mention, have a zero copy optimization internally. For people who care about performance, if you write into an empty pipe or an empty message queue on which there's a reader, it'll directly copy the data that you're inserting into their buffer. That does make the code maybe more complicated than it needs to be, and I'm not sure that it's always a win for most apps, but it is a nice thing to mention. But it is worth pointing out that these are good choices. They overlap pretty badly. So I would, again, if you're in a space-constrained app, and a lot of us really, even on the big systems, even on audio TSPs, there's still concern about code size. Probably don't use both. If you can avoid it, just use a pipe. Pipes are more general. Pipes are straightforward. There's really very little performance advantage to message queue. There's a little bit of code size if you're only going to use one. So now let's move on. So we've got queues out there, and we're going to come back to talk about queues in the context of Kpoll in a bit. But I did want to go off on one kind of discussion about race conditions that are real common when using these queues. So the basic idea of the queue, right, is you've got stuff that's coming in. You grab your thing, you do it. You grab your thing, you do it. You grab your thing, you do it. It is extremely tempting to have logic around that might condition the extraction from the IPC primitive, right? You're going to read from the pipe only if this condition is true, or you're going to read from this pipe under these circumstances and this pipe under these circumstances. And virtually every time you do that, that is a bug. I've tried to be clever and include some sample code here that does it in a non-obvious way. Basically, this is exactly the sample code you saw before about the FIFO queuing code, but it has a little switch box kind of thing, this set queue thing that can change the current queue that you're using. And because there's no synchronization around it, you say, okay, well, it looks correct because everything is just one line of code, but of course it's not. The load of that curve FIFO value from memory is happening at a different interruptible moment from the use within the kernel that's going to put your thread to sleep. Therefore, the explanation here is that the FIFO can change. That's probably causing a deadlock. Like for example, if you're about to insert something into the queue, and you got your thing, you figure out which queue to insert it into, and then boom, the thing changes. Before that happens, you're going to drop it into the old queue, not the new queue. Maybe it'll be forgotten forever, who knows. There are all kinds of bugs you can have here. But it's a fundamental problem with queuing as an abstraction if you're going to put this logic around it that says, which queue to use, when to use it, how long to wait, that sort of thing. Almost anything you do is either going to be a race condition or it's going to be isomorphic to the polling problem we talked about earlier. And then there's a note there at the end that, well, it sounds just like a data race, right? I mean, you just need to make sure it's locked, right? But there's no place to put the unlock call because that happens down in the kernel. You need to make sure that when the kernel puts you to sleep, you're still locked. But as soon as you're asleep, you can't be locked anymore. And so what do you do? And what you do is condition variables. And again, this is a textbook discussion that I think most people have already seen at some point, so I don't want to spend too much time on it. Condition variables are, in a sense, the most general IPC primitive. You can implement other primitives in terms of condition variables. The opposite is not true. And their basic abstraction is just go to sleep and wake up, or just like anything else. But the addition that they've got is that they've got a lock that is atomically released at the moment where you wait. So you've made your decision to go to sleep for whatever reason, and you go to sleep and release the lock without any opportunity for anybody else to get in the way. And that solves the problem, and it works pretty well. In fact, it works so well, we've actually seen it before. Right? The discussion here is about Kconfig, which is a top-level API primitive. But this is, in fact, that spin lock plus wait queue is exactly the same metaphor. And so the kernel is doing this already for you in order to implement Semaphores and, in fact, everything else within the system. Yeah, use this. I mean, this is, if you've got a complicated synchronization problem, and some problems really are complicated, this is what you want to use. I mean, and the rules are pretty simple, right? You take the lock, you do whatever it is you want to either decide to wake somebody up or decide to go to sleep yourself, and then Kconfig wait will release the lock for you and go to sleep, or Kconfig signal to wake somebody up. I don't have any sample code here because there wasn't space on the slide and I'm running out of time. But you do recognize the rules are simple. The implementation really isn't. This is complicated synchronization. You need to do it if you've got a complicated problem. But you need to know that you're in that space. At that stage, there aren't any really easy things. And so is that the end of the story, right? I mean, you've got condition variables, you now got the most common ones. Well, there's one real common case that people tend to see a lot of, that doesn't really need a condition variable, but it does need something. And that's, you've got more than one thing, right? You've got a main loop, right? This is like every app has this somewhere, right? You've got stuff that can happen. It might be, network packets coming in here. It might be keyboard events over here. It could be app-defined timers, upping a semaphore somewhere else. All of this stuff might happen. You just need to wait for the next thing to happen. You don't care which one it is. And a naive way to do this, you don't need a condition variable for this. You don't need anything fancy at all, right? You just have a whole bunch more threads. Each input can have a thread. They then demultiplex into one command pipe, main loop pipe, whatever it is, and then each one does its own thing. That's wasteful. Most people aren't real happy with that. I mean, again, a thread is the most expensive thing you're gonna ever use. You're looking at 4K or so for a thread stack. So we do provide Kpoll. Kpoll does exactly what you expect it to do. It works with a bunch of, but not all of the existing IPC primitives. You can use Kpoll signal, which is a user-specified one. There is a gotcha where the others are all level triggered. That is to say, if you call Kpoll and it says, okay, this one's available, then you don't do anything with it. You don't read it out. You call Kpoll again, you get the same thing. Kpoll signal is one shot. The app is required to have reset it, so you need some logic in order to recognize that you've reset it and that it's still there. It is pretty big and heavyweight. I do include the link to the docs because the sample code is too large. We also have, and I'll go very quickly at this stage because we're starting to run out of time, but we do have Kevent. This is a comparatively new tool from Peter at Intel, which does a lot of what Kpoll does, but without a lot of the complexity. It's much smaller, much simpler, easier to understand. The name is a little weird. I think it actually comes from FreeRTOS. They have an event group abstraction, which is very similar. It's just got a word. It's just a bit mask of 32 possible events. You can signal any of them that you want just by specifying a mask. You can wait on any combination of them, again, by specifying a mask. And it'll wake you up when any of those have occurred, and then you can go and then pull them yourself. It doesn't, the events themselves are signaled directly from app code. They don't interoperate with existing abstractions, but they are there. And so final important point here, and I think I'm going to get barely through this. What about user space? So the simple answer is everything still works in user space, right? You set user space equals Y. All the IPC primitives become kernel objects, right? They're all living in kernel side memory. They're all just handles that you use. All of the calls become syscalls. Everything still works. The problem is that the performance characteristics of the system completely change. Where I was like, remember I was boosting KSM earlier is like, please use this for a lock because it's like a dozen instructions. Now it's like, change a whole memory map. There's a couple hundred cycles to do that. On some systems there are cache effects. It's a big mess. And so all of a sudden, you don't really, a lot of these things about which you might be making these kind of weird decisions about, I need a message queue or a semaphore, none of that really seems to matter anymore because everything is bound up in the overhead of doing the system call in the first place. Which is to say, it sort of starts to look a lot like Unix. A lot of the same intuition about app performance starts to obtain, right? Like, where if you look at standard I/O, like you do a printf from a Unix process, and the printf does not, it's got 16 bytes of output, it does not have a new line in the middle of the stream. Your libc is going to say, you know what, I don't need to call a write system call. This has more stuff coming behind it. I'm only going to flush when I see a new line or when I get beyond my buffer size. All of this sort of thing starts to become more important than the actual IPC APIs themselves. And pipes start to look a lot better. In fact, if you're doing something from scratch, worrying about IPC and Zephyr, you probably want to be using it entirely with pipes. And then final important thread, slide, I'm going to go through some other stuff real super quickly. Is that unavoidable? Like, can we get back to the fast user space IPC we used to have? And the answer is, in the uncontended case, kind of, right? That semaphore, remember we were mentioning, has a count, right? If the semaphore count is 1 and you lock the semaphore by moving it to 0, you don't really need to talk to the kernel to do that, right? You just, just decrement it, right? And somebody else will notice that it's locked. Likewise, if you're upping a semaphore and no one's waiting on it, you don't need to do that. So there is, in fact, a syssem primitive in Zephyr. It works exactly like Ksem. Unfortunately, it is different code. It is based on a different kernel primitive called Futex, which, for the Linux people here, is basically basically a duplication of the simple modes of Kfutex, of Linux Futex. It's a little bit slower when you've got no user space used. It is a little bit bigger. It would be nice if it was kind of all the same. And I did try once, and this Zinc patch still exists. And if I'm nagged enough, I might try to dig it out. The problem is Zinc was, in order to handle all of the various edge cases, it ended up being a little bit bigger than existing Ksem, Kmutex, Kconvar code. And it was kind of violating its own design point, and it needed a little optimization. There is a sysmutex, don't touch it. Sysmutex is a wrapper around Kmutex. The priority inheritance problem that I mentioned earlier is fundamental, and it requires that the kernel know who owns the lock, and that is not something you can do from within a user space context where you can only change untrusted memory. So you'll end up with the kernel essentially handing priorities out to the wrong people, and so we can't really make sysmutex work. It's there, it does work, just don't use it. That's not something that we're going to be able to deal with. And just blasting through the rest of this stuff. Oh, and Maureen is saying stop. All right, but we do have POSIX. We've got mailboxes and stacks. Nobody wants to use those. And then, well, you can look at the complaints. Mailbox is just simply older. Stacks are weird. So you can use stacks. Stacks are perfectly safe. Mailbox is not. Final recommendations, just to sum up the stuff that I think is important. Use the subsystem IPC if that's what your app is based around. Right? If you're writing a Bluetooth app, stick with the Bluetooth framework. Don't try to do the interop yourself. Likewise, if you're porting POSIX code, stick to the POSIX stuff. Lean very heavily on the simple abstractions, Semaphores, queuing for other stuff. If you do need to do the multiplexing of inputs, K-events probably preferable to Kpoll. Never predicate your blocking calls. We mentioned that earlier. Don't get fancy. And if you do need to get fancy, start with condition variables, because I guarantee that if you're just worried that the fit isn't quite right around a synchronization problem. This is one of these very, kind of rare circumstances in computer science. If it doesn't seem like a good fit, it's actually probably wrong in synchronization. So do worry about that. And then come find us on Discord. Some of these questions are pretty straightforward, but I do find a lot of stuff gets left until code review, and it's good to be able to pontificate in a less contentious environment. All right. And I don't think we have time for questions, so I guess we're all done. Something like
Checking. It seems to work. Okay. Hi, everyone. I guess we're about to start. So let me just hope you can hear me fine. Is the mic working? I guess it's working. OK. So hello, everyone. My name is Zephyr. I'm working at Antmicro. The topic of my talk today is automated simulation-based flow for low-cost FPGA-accelerated devices with Zephyr on Beagle 5 Fire. I will try to cover multiple different topics with this talk. It will definitely not be as technical as the previous one from Andy about IPC or the previous one about Zebus, which was very interesting. It will be on a higher level of abstraction. But I hope you will find it informative as well. A few words about us. Antmicro is an open source software-driven company. We do a lot of hardware. We are heavily involved with RISC-V. We are one of the founding members of the RISC-V Foundation. We are very heavily involved with Zephyr. We maintain RISC-V in port in Zephyr. We also do a lot with tooling around simulation, FPGAs, ASIC design, and that's part of the CHIPS Alliance. Why am I mentioning this? Because what I want to highlight is that we work with the whole stack of technologies. That gives us, it puts us in a fairly comfortable position of working with various different technologies that are not necessarily in the typical toolset of software developers. And that would be one of the aims of today's talk, to bring these topics a little bit closer to people who are not necessarily very familiar with them. Originally, this talk was also supposed to be led along with Conor Paxton from Microchip. Microchip is also one of the founding members of RISC-V. Originally, back then, it was Microsemi, and they were the largest semicon to come into RISC-V. And well, it seems it did very good. They have the PolarFire SoC. That's the first SoC FPGA on RISC-V. I will talk a little bit more about this particular SoC in a moment. But it's a pretty beefy platform with an integrated FPGA fabric. We have been working with them. I believe we started in 2017. We've been working on Reno simulation for PolarFire SoC for RISC-V. We have been integrating our simulation framework with their IDE called Soft Console. And we have been working on customization features, allowing you to combine, let's say, classical SoC simulation with the FPGA part. I will cover all of these in a second. I mentioned Renode. Renode is our open source simulation framework. We support platforms from the whole range of available hardware, starting with small MCUs, ending up with beefy multicore machines. One of the key factors of Renode is that we aim to simulate whole systems and whole products. So you don't have to focus on simulating just the core. You focus on the whole platform along with its peripherals, along with sensors on a board, or with some actuators that you might have. So the whole product can be simulated, and you are able to run the same binary you would normally put on hardware. We support multiple architectures, so of course RISC-V, and that would be the main topic of today's conversation, but also ARM, Cortex-A, M, and R, OpenPower, Spark for those of you who fly to space. Zephyr Renode is software agnostic, but I will show that with conjunction with Zephyr, it really gives us a really nice result. And while we can run any type of software, Zephyr really is a very good match for running along with Renode. Tons of debug features, tracing, well, GDB debugging, of course, also in multi-node scenarios. All of this is available open source. So going back to PolarFire SoC, I'm sure you cannot read anything from this diagram, but the idea is that it's a really big platform. So 5 cores, 1 monitor core, and 4 application cores, all of them 64-bit RISC-Vs. Tons of different IP, different communication interfaces, but also the Fpga part. And the Fpga part is something that, well, sometimes makes people a little bit scary. They don't necessarily know what to do with that. But yeah, we'll try to cover it in a second. Originally, when Microchip released PolarFire SoC to the public, the original kit was called Icicle Kit, and later on they released a video kit. So both of them are a bit on the expensive side. So the Icicle is about $600. Video kit is $2,000. So if you're just an amateur or want to try it out, they're probably not the easiest pieces of hardware to obtain. But what is definitely worth underlying is that they were really produced mass market. And while there were boards from Sci-Fi, like Hi-Fi Unleashed, and actually the PolarFire SoC has the same CPU as Hi-Fi Unleashed, well, this is definitely much easier to obtain. But yeah, the cost part is definitely a big issue here. So enter BeagleFi Fire, which is definitely more on the affordable side. I believe it's about $150. So you probably are all familiar with the Beagle board and all the boards they produce. The form factor and the connectors are fairly known and follow their typical factors. There is a wide support from the side of documentation. There's, of course, a big community around BeagleBoard. The design is open source, and it does have support in Renode as well. What does it mean that we have a support in Renode? This is a short list of peripherals that we can support running in Renode. So if your software uses, I won't read the list out loud because it doesn't make much sense, but any of these, you can easily run this in Renode. PCI EU is with a little asterisk because I would call that a basic support. The idea of adding PolarFire SoC to Renode was interesting because it was there before the silicon was on the market. So we were working with Microchip, adding these models, and as soon as they have announced the platform and released data about it, we were able to allow people to simulate their software in a virtual environment, beginning the development of their solutions early before they were able to actually get hold of the hardware. Because, of course, the SoC itself was released at some point, but before the hardware platforms were available, well, some time had to pass. So, yeah, we have quite a few RISC-V platforms available on the market. Why is it special? As I mentioned, it's 5 core, 5 64-bit cores with a fairly standard instruction set support. Gigabit Ethernet, USB, various different connectivity options. But I guess the FPGA fabric is the thing that makes it stand out and gives you the possibility of expanding the capabilities to various different areas. When we were submitting this talk, BeagleFi Fire was definitely one of the easiest options to obtain affordable version of PolarFi SoC. But of course, time is moving forward. Microchip has announced its Discovery Kit, which will be in the probably similar price range, about $150. We have also made an open source system on module, which you can download all the details of from our GitHub and look it up on our open hardware portal. PolarFi SoC comes with different FPGA sizes, so you'll have to take that into consideration depending on what your needs are and what are your planned applications. You might want to choose different options. But of course, there are other platforms as well. If you type in Google PolarFi SoC module, you will get tons of different results. Not all of them will be available for buying, but yeah, it's definitely getting some traction. So, but I guess that the bottom line is that what BeagleFi Fire caused is that this work with RISC-V and FPGA solution is no longer gated by the high cost, high price tag. But there is a discussion about the ease of use. Not necessarily everyone is familiar with FPGA topics, and there is some entry barrier to that. Why should you even care? Well, of course, the SoC itself is really powerful. You can do a lot with it. You don't have to care about the FPGA part. If you don't need to, you can just focus on the ASIC part and run your Linux or Zephyr or any other piece of software you'd like to. But of course, what the FPGA parts adds on top of that is the ability to expand the capabilities of the base platform with whatever you actually need. So typically, the usages would span from machine learning accelerators, some crypto mechanisms, some security mechanisms, image or video processing. Any processing that can be easily parallelized is a good match to put on FPGA. If you're interested in power efficiency and high-speed processing of signals, that's definitely something you can focus on. And of course, there will be dedicated solutions. You can buy a platform with specific DSPs that do whatever you need or specific ML accelerators. But if you need a custom solution, then FPGA is the way to go. So, give me a sec. When Microchip released, first of all, Microchip contributed BeagleFi port to Zephyr. I believe that was the end of last year. And when they released the PolarFi SoC in general, they have also promoted their IDE. It's called Soft Console. It's based on Eclipse. We have been working with them on integrating Renode into it, so it's quite easy to just press play and have your software running on hardware or in Renode in a simulated environment. If you want to have any FPGA-related payloads, of course, you have to program them first. The IDE does not really help you with that. Microchip offers other tools to do that. This is very convenient to use. Press play and everything works fine. But this is probably not what Zephyr developers are used to. So typically, your workflows would look a little bit different. So yeah, the IDE is there, but it's probably And yeah, I have to underline that Microchip also has released debug configurations to run Zephyr applications in soft console and debug them easily. But still, this is, let's say, a fairly non-typical flow. Let me take a small detour here. Why am I even talking about Zephyr in this context? Of course, you can run any software on Beagle 5. You can simulate any software in Zephyr. Why Zephyr is an important part of this talk. In general, an RTOS like Zephyr, that is dubbed as batteries included, is aimed to enable all its features on different hardware platforms in a fairly easy, configurable way. And I can definitely testify to the fact that Zephyr does that exceptionally well. So we have the modularity of the RTOS, so we can turn features on and off. You can pick and choose whatever you need in your application. You have discoverability of features that are available on your platform. For example, in the build system, it's very easy to verify if your platform does support specific features. With the hardware model version 2, which was a recent very large change in the way platforms in Zephyr are described, this is even more prominent. Zephyr has device trees. By the exclamation mark, you may notice that I'm pretty excited about device trees. We use them in various different contexts, and I will tell you why in a second. Yeah, so how do we take advantage of this? So if you have listened to some of our talks in previous years, you might be familiar with some of the work that I will just mention right now. I will start with the Zephyr dashboard. This is our CI system where we take device trees from Zephyr, try to generate descriptions for Renode platforms, and run several sample applications, ranging from Hello World, which is, well, admittedly fairly trivial, through more complex like shell sample or MicroPython or even some TensorFlow-like micro or canning applications where canning is our machine learning framework that is integrated with Zephyr as well. And we get to run 470 platforms as of this day, which is about a little bit more than 80% of whatever is available in Zephyr. We present all these results in a nice, graphical way. You can inspect them, replay them easily. And we use that for two purposes. First, to improve Renode, because we want to support as many platforms as we can, but also to improve Zephyr. We have a CI that runs daily on different versions of Zephyr. We are very quick to detect any regressions. Also, when the move to the hardware model V2 took place, we also were able to detect some regressions with that. We had improved the RISC-V port quite a bit with this work, et cetera, et cetera. So yeah, this is what we get from using device trees. We can analyze them. We can create simulations from them. And of course, this is not specific to Zephyr. We can do that for UBOT as well, or for other software payloads. What we need is a unified way to create software. So the best way would be a single command to build software for a target, and a way to describe platforms in a machine-readable way. So UBOT Linux is also a good target, probably also other targets out there. With all these CI systems that we're running, we get a lot of data about the systems. We are putting them together in Renodepedia, which is our platform or a portal for presenting this information that we learn about different IP blocks, SoCs, boards, all levels across this whole landscape. We try to present them in a structured way, creating a catalog, if you will, of hardware components. Very easy to navigate, shows how to run things in Renode and presents you with different software payloads if you want to run them yourself. So getting back to this slide, I take device trees. I create some CIs with this. I get to create a lot of different pieces of information, put them together. But this is, well, slightly, I would call a passive approach to data that we have in Zephyr. What we are working on now, and what I will present you live in a few seconds, is a more proactive approach. So given the fact that Zephyr platforms are based on device trees, that means we can leverage this knowledge and leverage the knowledge about specific blocks and how they are connected together, how to create new device trees and create new platforms that are not yet available in Zephyr fairly easily. And Visual System Designer is our tool that allows you to create platform description in a fairly formalized way based on building blocks that we have gathered from or created from our, well, few different sources, like the dashboards that I showed you or Fpga, but also our hardware work with open source hardware designs, where we have a large library of components that we can put together to create fairly complex and complete descriptions of systems. And going back to Beagle 5 Fire and Polar Fire SoC. As I mentioned, the topic of FPGAs is not always familiar to also software developers, and there is always some barrier of entry to get started with FPGA payloads. And of course, there are different ways to interact with IP that is loaded on FPGA, but we will focus on one of them in a second. There is a big trend, and of course, our work in Chips Alliance is also following this or even paving the way for this trend to create more and more open source IP available for the users out there. So this is not something that you can, if you want to have a specific peripheral block modeled in your FPGA, you don't have to go to your vendor, buy it for $1 million, and then try to integrate in your FPGA system. You can use blocks that are open source, publicly available. When you create a FPGA IP, you write your code in a hardware description language, a Verilog or VHDL or Chisel or, well, there are many right now. And when you have this description, you can compile it with Verlator as one of the available tools. It's a popular simulation tool for Verilog. And you can customate it with Renode. So we create a simulation where part of the system is described in Renode, part of it is described in RTL directly. So it's generally not very difficult, but if you would like to hide this complexity and make it work with your software fairly easy, we can try to use our VSD system designer to make it a little bit easier. And I will push my luck now and try to do a live demo. Nothing can go wrong, obviously. That's how live demos work. I will use a self-hosted version. We are, if you have seen the presentation from Michael last hour at the 5th floor, you might have seen our front portal that will kind of expose it in a well, online way. Let me start a self-hosted version first. So this is the Visual System Designer. What you see in the middle is, well, of course, our workspace. And on the left, there is a large library of components. Of course, I will not create a Beagle 5 file description from scratch, because that would take me, well, some time. But I have it prepared. So yeah, this is a graph that describes the platform. As you can see all the details in the screen, and you probably can't see that, but I have a zoom wheel here, right? Zoom is so cool. So this is the PolarFire SoC SoC, and it's connected to multiple various different devices. So you have something connected to I2C, something connected to GPIOs. Here you have M2 connector connected somehow. And a lot of data. A micro SD connector. Here is Ethernet, etc., etc. You have some buttons, you have some LEDs. The whole system is described here. What can we do with this? Each of these blocks, well, not each, because some of them are not really important from the perspective of your software. But the ones that have associated device tree entries. So we know how to describe them in device tree. So what I can do right now, I can press play. And yeah, now is the part that should not break. Let's hope. Yeah, live demos. OK, yeah, it works. So what happened just now? We took this diagram. We put it. We put some warning for blocks that are not supported in this flow. Of course, we can describe more than we can simulate, which is fine. We are building a device tree out of it. We are building Zephyr. If you have ever built Zephyr, you're pretty familiar with these types of logs. And we are trying to run it in simulation. And here I have a UR0 and, well, probably something that you're familiar with. Help. Yay. And you have a, well, typical shell console. No Fpga included right now. I will close the simulation. What we have added in this flow is a little bit of a trick. If you scroll down, you see this Fpga node. This is supposed to be a connector for the memory mapped devices that you put on Fpga. You will notice that some of the things I will do right now are a little bit simplifications of what's happening in real life, but I will try to explain myself. So I'm looking for a specific UART block, but this could be any Fpga IP that I would like to simulate. I'm using a specific block named like that just to get some meta information displayed. So we have some information about this block. It will be labeled as UART8. It has some address pre-configured. I can use any other address, but for the demo, I probably wouldn't have remembered this specific address that we verified not to collide it with anything else. I also add a specific interrupt number because it will be connected to the interrupt controller. I will put it on the other side. And yeah, I can connect it to the Fpga connector as well. What if I try to connect it to something else? Well, I can't because the system is smart enough to know that it's not a GPIO, it's a memory mapped peripheral, so I have to connect it to this connector, if I manage to do that with my shaking hands. Yeah. All right. Of course, this is a block. When we are talking about IP, there is some RTL. I was telling you that we are compiling something with later, and I'm definitely not lying here. We have, well, admittedly, I have it precompiled, but we have it on our repositories. If you'd like to reproduce this flow, it's fairly easy. I have compiled the related block for this very purpose, and I have printed out the path here so it doesn't elude me. OK, so I have address pre-configured and interrupt number pre-configured just for the sake of the demonstration. I use some compiled RTL block. And I can use some settings that are typically reflected by device trees. Let's make it the default console and the shell UART. yeah, let's press play. Please note that this is UART 8, and well, previously we've been putting out things on UART 0. So this board does not exist in Zephyr at all. There is no board with light UART connected to at this specific address. But apparently we're already done, and so the Zephyr was rebuilt, and I have yet another UART that's actually using this related block. You will see it's very related because it's slightly slower to simulate. So yeah, you see that the output is, well, probably not very visibly, but it works slightly slower. To show that it's not like a prepared demo, I can even try to, for example, split the UARTs between these two, so between the default UART 0 and UART 8. So let me disable shell UART, press play again. Yeah, Zephyr is rebuilding in the back. And you see that, yeah, here I get the prompt, the welcome message, and on UART 0, I have the shell prompt because, well, we return back to default. And to even more highlight that it's actually working with the whole build system, let me go to this directory and show you what does it mean to have a board in Zephyr. Actually, not that much. So this is the data that we generate from the design itself. We have a dev config, device tree, Kconfig entry, board YAML, and this is only for the purpose of using the related block, and not that important. Let me go to the DTS. You will see that this is a fairly regular DTS with, you know, cores, etc., etc. It's not maybe as pretty as the ones that are hosted by Zephyr because it's auto-generated. So you'll see, for example, that when you go a bit down, you will see some blocks that could be in line with the others. But we are, of course, trying to make them on the fly. These are blocks that were created from the graph itself, so some LED, and the UART itself. So you have the UART, it's labeled as UART 8, it's a specific address, with interrupt connected to PLIC, interrupt number, etc., etc. And this is the entry specific for this particular block. And we have the chosen entries as selected by this graph. It actually matches, yeah, good. I didn't check that before, but it does. Kconfig and devconfig, they're not really that important. But this is actually everything what you need to get a board in Zephyr, right? So it's fairly trivial. Yeah, and the YAML itself, that was probably the last thing I wanted to show. It indicates what kind of SOC is there, name of the board, as specified on these in the graph itself, in the graph file that I loaded. So we have full control over what's going on here. Everything is created from scratch. So let me get back to the presentation and reiterate over what have you seen here. We have a powerful SOC. We have a graph that describes the whole board. We have the block that was not previously there, but we have added it. So from the software perspective, it doesn't really get any easier. Does it mean that you can take this binary, load on your BL5 platform, and it will run? Well, no, because you have to have the Fpga programmed as well. That's another set of tools. We're not covering that part yet, but of course, here we are focusing on the software part. The software has been built specifically for this particular platform, so you can see that I have been selecting and deselecting some of the DTS options to redirect the UART output one way or the other. Nothing here is vendor specific. It's pure Zephyr data. And the fact that the data is there and it's carefully maintained by a bunch of people makes it, well, us included, makes it very easy to follow this kind of flow. All of the data, including all of the blocks and that we put together and that describe the whole board, is open source. The whole processing part is also open source. And yeah, it's very easy to reproduce this locally and expand it to support more scenarios as well. If you want, you can go to our GitHub, find relevant repos, or ask me for them, and you will be able to contribute with your own data, making our nodes more specific or adding new hardware components, wherever you please. Where do we go from here? Michael's talk last hour probably covered the first point, and that we would like to expose a dedicated portal to users and have more people involved. We would like to enable more software scenarios. Of course, this was shell. Michael was showing a scenario with some sensors, temperature sensors, readouts, and blinking LEDs. Of course, this is fun, but that doesn't complete the whole, let's say, area of possible options here. IDE integration is something that we'll be also working on. You haven't seen well, this is web-based, so all modern IDEs are kind of also web-based. Integration is definitely in scope. Vendor independence, well, it's already there actually, right? So we're relying on data from Zephyr, and we definitely intend to keep that. So we're not trying to focus on specific platforms. We try to expand our interest to new ones and support as much as we can. This was a level of a board, so we had an SoC. We've connected different blocks around it, but we want to work on different levels of abstractions. So you should be able to design your SoC in this kind of system. You should be able to design your board as well, but also a device. So connect multiple hardware platforms, connect them over certain interfaces, and then when running this kind of simulation, inspect the status of these interfaces, inspect the communication, et cetera, et cetera. Yeah, if you're interested, reach out to us or talk to me, or if you have any questions, I would be very happy to answer. Thank you very much. I have a microphone here, so I should probably pass it to you.
Yeah, so that was a great demo. Thank you.
Thank you.
And I was just wondering, so by default, it executes on Renote when you press play.
Yep.
How about, do you also foresee doing the same but flashing onto real hardware? Have you, when you press play, or is that not in the works?
Yeah, it's a good question. I will try to run another demo that will show you that running in Reno is much funnier. But no, actually, it's not really a big issue to connect it to real hardware, right? So I would say that a lot of work is about exposing data from Renote and showing them here. So I was only showing the UART, but we can blink LEDs, or we can read temperature readouts from nodes that are described on the graph. But yeah, I mean, probably doing the hardware part would be the easy thing here. So I don't see any issues.
You mentioned yourself the programming of the Fpga, right? That would have to actually physically happen when you press play, correct?
Yeah, and well, there will be definitely more to that. I will just try to actually load the second demo. Up. Do I have it? Let's hope it works. OK, so this is a fairly simpler demo where we have an STM and LEDs, and it's not this demo. All right, so I will show it afterwards. So I don't have a full setup, sorry. I might try to run it very quick. Sorry, I shouldn't. I should say no, it can be done right now, but I'm too deep right now. Yeah, I'm here.
Pressure's on.
Yeah. I'm very fast. Yeah, I got this. I so got this. I will restart this one. I have it. It's almost there. Wow. Yeah, so this is a very similar, we are working on multiple branches right now. Oh, okay. It's not this one.
Maybe you should do the demo later.
I will try to run it anyway. We'll see what happens. So yeah, the idea is that we have access to all of these blocks, and we can read out the specific details. Yeah, so you can see that LEDs are blinking on this. With the hardware, this will be more difficult, right? We have some temperature sensors, which I can change temperature, and you can see that in the Zephyr logs because they are being read out. But yeah, the FPGA programming part is kind of vendor-specific, right? So there will be a lot of vendor-specific bits on that layer. So I try to focus on what is vendor-independent, which is software in that case.
My question was related to FPGA. So I mean, there is, as you mentioned, there is definitely a niche of people who are doing FPGA development simultaneously with Zephyr development, co-design, if you will. And for the Zephyr FPGA area, I think it'd be really useful to actually integrate some of the open source synthesis tools.
Oh yeah.
So that we could drop our RTL and our driver in the same directory and just do like co-design and co-simulation, that sort of thing.
Oh yes, absolutely. I mean, yeah, please.
I remember talking to Connor about this a couple of years ago at ZDS. Actually, yeah, it was a couple of years ago. Or no, it was a RISC-V summit, my mistake. And I'm just wondering if there have been any discussions about microchip supporting the open synthesis tool.
Yeah, I guess we're not necessarily there yet. This is still on a branch. But yeah, I think that in general, with the advent of open source synthesis tools, which we are working on a lot, integrating these flows together is definitely closer than it used to be before. We'll probably have to do some homeworks to gather fully, but yeah.
My next question, I just wanted to see what Jason Kreidner, his thoughts were, founder of BeagleBoard.
Sure.
Yeah, I would love to integrate with the CI flow that we have, right? So I don't know if we can start with, like, we publish a gateware in our CI so that people don't have to install Libero in order to build new gateware. So it'd be nice to kind of close that loop entirely, right? Go into simulation so you can validate your Verilog with running drivers and everything in the system, and then go back into do the generation of the bit stream, right? And then we have Linux command line tools for reprogramming the bit stream with that. And it'd be interesting to introduce bit stream reprogramming with Zephyr as well, right? So that it's not just in from Linux. But my question, so yeah, absolutely love to work on integrating this into our CI flow. But my question is do you do the same thing with Linux, right? Because you're running a kernel, I mean, an emulation of the CPU core. Can we do the same thing, generate the device trees, and run this with device tree overlays and Linux kernel? Yeah,
that's a very good question. So we're actually working on running Ubuntu on BeagleBoard Fire right now in simulation. We're, I would say, almost there. Some bits missing, but we kind of get to user space, and we need to get systemd to finish its startup. But in a more general sense, Zephyr has one big advantage. It's newer, so the device trees are of better quality. And yeah, really. And I don't have like a very strict data on Linux itself, but we're working with Ubuntu, which has very similar device trees, and of course it's aimed to boot Linux afterwards. And well, you find device trees that have no CPU, for example, because well, no one really cared about describing them in a device tree. And when we are trying to build a system out of it, we kind of need to know this kind of details. With a proper description, with good mappings from the compat strings to the drivers and our models, this is also definitely possible. Zephyr is just, you know, a smaller target. So I think it's a fairly easier first step. Right. Thank you very much.
Thanks, Peter.
Sure.
John Ryan from Microchip.
Nice to meet you, Peter.
I'm local here in Seattle. So
oh, great to meet you.
Yeah, unfortunately, Connor couldn't make it out.
Yeah, we kind of assumed that he won't be able to, and that's how we discussed it earlier.
Yeah.
But yeah, well, I should probably disable myself here.
Test.
Test. Test, test. Test. Test, test, test. Really close enough, isn't it? Did it work? Talking louder. Yeah, well, fair enough.
Test.
Yep. I don't know if I'm supposed to be, which one I'm supposed to be using, but I guess I'll try the other one and see if something happens. I mean, oh, there we go. Perfect. That shows up properly.
there a way to get rid of the arrows on the bottom in preview? Or maybe just present from Google Drive. I'll just open it as a PDF. It is PDF. Yeah. Oh, that's better. Yeah, cool. Ryan, are we supposed to have an AV guy here, or? Test, test, test. Test, 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 test. Ladder. It's about as close as I can get it with my neck.
Yeah, no,
It'll work? All right.
Do you need any computer audio for your presentation?
Any what, sorry?
Computer audio.
Audio, no.
Do you need a handheld mic for Q&A?
We will, yes, but it's probably down the back already.
Yeah,
Oh.
or if you have somebody that you wanted to.
Oh, there's the room host, Ryan, he's handling that. All right, cool, we'll get started. So, BiffEML. Just before we get into the presentation, I guess I've got a couple of quick disclaimers. So you may have noticed that the name on the title slide, the company does not match the name on the presentation, on the schedule. So all of this work I'm presenting here was done under the auspices of the CSIRO, which is Australia's national research organisation. I'm no longer an employee. I'm presenting this in a personal capacity. And all this work was funded by the CSIRO. And just for some of the numbers may jump around a bit for algorithms and stuff. There are multiple algorithms over time, and that's why they may not match up a bit. Especially in the ag tech space and machine learning and engineering, this is never a one-man show. There's always multiple people involved, lots of expertise. I'd just like to acknowledge Greg Bishop-Hurley, who's been the project leader for this, our main agriculture contact, and Reza Arabuli, who's our main, who was our main machine learning and research scientist. So, machine learning on cattle, why do we care? So, as I'm sure all of you are aware, cattle are a very emissions-intensive source of protein. But there's things that farmers can be doing to sort of improve that situation. Selective breeding is definitely one of those things, which is best, and the way that can be improved is sort of feed efficiency. So how much grass does it take for a cattle to eat for it to put on 1 kilo of mass? If you can improve that ratio, then the emissions per kilo go down. And some of these things are relatively easy to measure. Weight gain, for example. Walkover weigh is a relatively common equipment on farms. As many of you may know, that's not a cow, that's a sheep, but it's the general idea. They walk on a bridge, it weighs them. But the amount of food that the cattle eat, it's something that's much harder to quantify. Even if farmers wanted to stand around in the sun all day, they don't have the time or even necessarily the expertise to sort of measure how much is going into each cow. And obviously, each farm has hundreds, thousands, tens of thousands in some cases, cattle. So it's not a scalable solution. So if we're trying to calculate this sort of feed efficiency metric, how do we actually get out the amount of food which is going into the cattle? And in an ideal world, you can basically calculate this by how long was the cow grazing for, how often is that cow biting, and how much is that cow biting per bite. But what do we actually have to measure that with? And in reality, all you really have is an IMU. For a lot of this stuff like, and then from the IMU, you sort of try and calculate how long the cow was grazing for, how much it's biting, and then you sort of apply some scaling factors of how efficient is this pasture, essentially. Right now, we're basically just using IMU data. In an ideal world, you would have a measure of what sort of pasture is this cow grazing in, how good is that pasture, i.e. if it's rained over the last month, you're gonna have nice, thick, lush grass. If you're in the middle of a drought, it's gonna be quite sparse. And that's really gonna affect how much dry matter is actually going in. But this talk is really about the machine learning magic in the middle there. So given IMU data and some magic, how can we get out to time spent grazing and a bite rate? So obviously to have machine learning on cows, you need some hardware. And this project utilizes 2 main categories of hardware. So one of those is a research collar. So this is a big collar that goes on the cow's neck. I've got some photos a little bit later on. It's had many iterations over the years, all of them except for the Loki 2 of running Zephyr. So that's been a really great transition for us. But even the collar with its relatively large size is still quite resource constrained, right? You've got 1 megabyte of flash, 256K of RAM. And these things have to sort of be able to survive for multiple months out in the paddock without really any human interaction. So they are indefinitely powered off solar. They've got a relatively beefy lithium-ion battery in there, and low-power IMU, contact logging, and they log all this data to SD card. And the other useful information there is, I guess, is the sort of 1 hertz GPS trace. So over the course of months, you can track where these cows are going over time. The second piece of hardware, I guess the other thing we should note about this is that this is a relatively expensive piece of kit. It's a big collar, you got weights, you got webbing for the thing which goes around the neck. So it's not a scalable solution, and they have a tendency to fall off over time. The fabric gets ripped. So it's not a scalable solution. It's a great research platform. But for selective breeding and stuff to take place, it needs to be a scalable solution, right? So that's where the second product comes in. So the Series Tag is a commercial product. This has got one in my hand. Again, it's a resource-constrained platform, 1 megabyte flash, 256K RAM. As it's a commercial thing, it goes on the ear of cattle. Again, it needs to run indefinitely off solar power. So it's got a rechargeable LiFi battery in there, low power accelerometer, super light. less than 30 grams. It was originally designed for cattle, but as you hopefully can see in the ear of that giraffe, that's not the only place it's been deployed. I guess the other cool thing about this platform is that up on the top right there, you can see it's actually a direct-to-satellite platform. So it doesn't matter where in the world these tags go. There's no infrastructure required. It can report its location up to 6 times a day, direct through satellites, which is pretty cool. And until it was made, not many people thought it could happen. So obviously, to have a machine learning algorithm, you need data to train that algorithm on and to validate what you're generating. So this has been a project inside of CSIRO for a long time, over more than a decade. I think up to now, there's been sort of over 100 sort of multi-month deployments of these collars all across Australia. There's even one currently going on in Switzerland. And each of these deployments is sort of consisted of, you've got the raw data being saved to these collars, but you also need annotated data in order to train these models. And depending on the experiment, this can be anything from 24/7 video recording with later annotation. It can be farm workers wandering around with a notebook and going, this cow is eating now, this cow is drinking now, etc. And then you've also got the automated data, so the walkover ways are a good example of that. But the data collection is actually a big problem for the ear tag solution, right? These things are ultrasonically welded shut. They're completely sealed. You can't get out of them. And they've only really got enough data on there for maybe a few hours, sorry, enough space on there for maybe a few hours worth of data. So what we actually do is we have when we're generating data, we have an ear tag together with a collar. Those two things pair over Bluetooth. And the ear tags actually stream their raw accelerometer data over Bluetooth to the collar and save that data directly onto the collar's SD card. So at the end of the trial, you pull the collar off, decode the SD card, and then you've got your 2 different data streams, one for your collar samples and one for your ear tag samples. So just to give you a bit of an idea of what a trial like this looks like. So on the left there, we've got an example of a bunch of collars. So that sits on the neck. You've got the webbing which goes around the neck of the cow. And then down the bottom, you've got a big weight to sort of try and make sure that that thing stays on the top of the neck. Cows come through the, this is not a walkover way, this is a crush in this case. But basically, it compresses their sides so they can't move too much. You install the hardware, off they go. So after you've installed it, you've got a bunch of cows. It's probably worthwhile noting that even though these things have literally just been deployed, there's quite a lot of variation in like how those collars are actually sitting on the animals. And you can also see ear tags in the ears of a lot of those. And then once they've been put through the crush, they're put back out to the pasture or whatever. In this particular experiment, they're being fed out of bins, and these things automatically track which cows are eating from which bin and how much they're eating at a time. So it's a way of ground truthing the algorithm. And then obviously, once they've been put out, you don't want to sit there and watch for 3 months while the cows eat. So we have some remote monitoring dashboards for where are the cows currently, what are the battery voltages doing, how much data is being logged, etc. So you can sort of go, okay, well, maybe this 1 or 2 collars is having problems, need to go out and fix that. If everything's all good, just let it run. I guess, so currently, this data is all sort of reported through LTE. In the past, it's been through LoRaWAN. We just sort of use whatever makes sense at the time. So data processing. So we've got our data. What does our sort of processing pipeline look like? So we've got all our data on the SD card. We've got a bunch of annotations from a whole range of sources. We decode that binary format into a whole bunch of CSV files, too many to be honest, probably. And then we've got to sort of all rationalize all that data into a common format, which like Python training tools can use, for example. So there's a whole stage of pre-processing there. Then there's the actual iteration over the machine learning architecture. It's a lot of heuristic stuff. I think the next slide goes into a bit more detail. And you sort of validate the architectures you validate the architectures you're looking at against the data sets you have. After you've done that a bunch of times and you've sort of hit your either local maximum or hopefully global maximum of performance, you output the model structure and the model parameters ready to be put onto an actual embedded device. And you need different models because they're different devices. They're attached to the animal in different ways. So if you tried to run a collar algorithm on an ear tag, it's not going to go so well. So there's a whole range of algorithm tweaking points of ways of how you want to design this. We are focused on ultra low powered devices, so the main constraint is how long does this thing take to run, and will it fit inside our memory? Obviously, a large language model is not going to fit on these devices, so it's an important process. Yeah, lots of features to tweak. It's not my area. I'm not into the details of it, but it's basically a combinatorial optimization problem. So you are trading off all these various issues to try and get the most performance you can out of this thing. Once you've got your algorithm, you need to obviously validate how well that matches the data you've generated. So to do that, there's a thing called n-fold testing. So you've essentially got your complete labeled data, and then you subdivide that. So this will be four-fold testing. So you subdivide that into different slots. You train your architecture on, say, 3/4 of the data, and then you evaluate it on the last quarter. You combine all those folds together, and you see how well that would have performed overall. And yeah, that's the iteration of the architecture of the algorithms. Now, there's lots of challenges with trying to design these sorts of low-power algorithms. Cattle are not necessarily cooperative test subjects. As I mentioned, the collars move around on the neck, ear tags move around the ear. In extreme cases, cows can bite through the collars of other cows. It's just a mess. Unbalanced data sets is also a real issue. Cattle don't spend the same amount of time grazing as they do drinking, as they do walking. They spend many hours a day grazing, but maybe 5 minutes drinking. So it's an important thing to recognize when you're designing these things. You could say it's 95% accurate, but it gets all of the drinking completely wrong. So you've got to be aware of that when you're evaluating the performance. MEMS accelerometers are also not ideal devices by any means. They have a whole bunch of variations with temperature. They've got nonlinearities, cross-axis sensitivity. Basically, what our machine learning guys said is basically individual samples are worthless. What you have to do is look at statistical properties over a window. If you're looking at individual samples, all you get is noise. And gyroscopes are apparently even worse. To date, we don't use gyros. We collect gyroscopic data, but the energy cost is not worth the, if any, performance gains. So how does this thing actually run on a device? So at a high level in our Zephyr application, we've got a task scheduling and configuration thing. So that controls sort of the parameters that the accelerometer is set up with, for example. So run at 50 hertz with a ± 4G range or whatever. That's reconfigurable on the fly. Also controls GPS and environmental sampling and everything else. So this scheduling basically triggers the IMU thread to run. That runs the IMU, generates data in big chunks, and shoves that off to our own data broker, which is basically Zebus, but written a few years before Zebus was out. At that point, we have a range of algorithm implementations which consume that data. They run the algorithm over the data and put outputs. And out of both the IMU thread and the algorithms, the outputs of these things are logged to both SD card, pushed out over Bluetooth, and reported back up over LTE in this case. The actual thread itself is relatively simple. It sits there waiting on, it's probably quite recognizable if you've used Zebus. You sort of sit there in the thread, you wait for new data, iterate over the samples, buffer it. Once you have enough data, you run the algorithm, log the outputs, clear the buffers, repeat as needed. the actual implementation of this is all just done, well, 90% of it is just CMSys DSP. It's available straight in the Zephyr tree, super handy. And basically, the operations from, say, PyTorch map pretty directly to the CMSys DSP functionality. If you have some form of hardware acceleration, you even get free hardware acceleration with the DSP stuff. So yeah, so even stuff like convolution, matrix multiplication, hyperbolic tangents, it's all pretty easy to get going with. So for us, we sort of separated the whole process into two parts. There's the feature extraction and the classification. And then both of these C implementations are actually unit tested against outputs from PyTorch to validate that the performance you get in Python is actually the same as what you get on the end device. And that actually works really well. It makes it super easy to see whether your implementation is actually correct, because you can get it to basically identical outputs, even though one is Python running on your x86 and one is Cortex M4. We implement it on 32-bit floating point numbers. Our Nordic chipsets have a hardware floating point unit, so that makes that relatively efficient. We have in the past measured or attempted to implement, well, attempted. We have implemented it in quantized implementations, so 8-bit. You do get faster runtime. The weights are obviously much smaller, 8 bits versus 32 bits for the floating point. Your accuracy does go down very slightly, but not really enough to matter. But the main problem is that it's significantly more painful to implement. Because it's a quantized implementation, it saturates basically immediately. So especially if you're rapidly iterating on algorithm implementations, the cost of doing that is significant. So up until this point, 32-bit floating point numbers, and the performance numbers I'll give in a couple of slides' time sort of show that it doesn't really matter in the grand scheme of things. So depending on the model architecture you have, they can be very ROM heavy. For example, the example I had in the previous slide was 40 kilobytes for the model parameters. But that's basically driven by how large is your feature vector and how large do your matrices need to be. Obviously, matrix size is like a square thing, so if you can reduce that by a little bit, you get quite significant size savings. In terms of RAM as well, you can reduce that quite a lot through intelligent reuse. For example, the architecture shown down the bottom there, you can sort of see that for each axis, once you've done the operation, you don't actually need that previous data anymore. So you can actually just ping pong your data back and forth between the buffers for each step. So you only actually really need one extra buffer here to hold all of your however many kilobytes of data. More complex architectures obviously need a bit more RAM, because you can't just ping pong back and forth, but you don't need 12 buffers of 4 kilobytes or whatever. So how does the thing actually perform in terms of efficiency? So the algorithms run over 5 seconds worth of data, but the whole process of the algorithm itself only takes about 20 milliseconds. So it's that's it's quite different from what you might imagine from a large language model where you send off your result, a whole data center GPU cluster runs on it for a second or two, and you get back your response, right? It's much more efficient, and the weights and the DSP functions themselves are also really efficient, right? This entire algorithm is sitting in more or less 3 kilobytes of ROM. And what that actually lets us do is have multiple algorithms compiled into the application at once, and then dynamically switch between them at runtime, depending on, for example, which breed of cattle the collar is on at that point in time. Yeah. So how does it actually perform, like in terms of accuracy? Now, as I sort of mentioned earlier, it's a nuanced question to answer because you can say it's 95% accurate, but really it might just output grazing for every sample, right? So a better way of looking at that is this thing called a confusion matrix. On the left-hand side there, we've got what the animal is actually doing, and down the bottom, we've got what the algorithm is predicting. So it's quite easy to see here that the data sets are in balance. You can see that grazing and ruminating are far and away the largest, the most data points that we have. But in terms of like the errors as well, it's also interesting to look at what things are being mispredicted as. So for example, drinking, you can imagine a cow drinking, it looks much closer to an animal grazing than it does an animal walking, right? So trying to differentiate between these two behaviors is quite difficult. And you can see that in the, like how often drinking is misclassified as grazing, for example. Yeah, but at the end of it, you essentially get what was that cow doing for that window of time. You can push it over LTE, and then you get out a nice graph of what the animal is doing. I have no idea how long what timing is. 23 minutes, all right. I guess, any questions? Colors.
So you used CMSIS DSP directly. Why not use TensorFlow or one of those machine learning libraries that are available also for embedded systems?
Mostly because the machine learning part was done in Python. It wasn't done in TensorFlow. I expect if the training was done in TensorFlow, exporting that to TensorFlow Lite, for example, would be easier. But the models themselves are not that complex, as you can probably tell from the 20 milliseconds of execution time. So the cost of just writing the CMSIS DSP and unit testing it is relatively low in terms of effort. To get you get a new algorithm, new weights, new features. It might take an hour or two to do up the CMSIS DSP. It's not a huge overhead for the sort of stuff we're doing. If it was like image DSP, like feature, like digit extraction, I imagine that would be a nightmare to try and do in CMSIS DSP. But these things are small, they're compact and efficient. CMSIS DSP is what we've been using for that.
Right. One more question. Can I ask one? Sorry, yeah, one more question, just out of curiosity. I assume you have your own app repo with all of these libraries, the application itself, of course. Yep. And out of curiosity, did you systematically update the version of Zephyr you were using, or did you stick with one for the whole duration of this process?
Well, so as I sort of alluded to, this has been a sort of a decade-plus project. Right. The first research call was running Kpoll, not Zephyr. Then it went to FreeRTOS, and then finally to Zephyr. So as new releases come out, we have new application versions. It generally tracks the latest Zephyr release. Sometimes it falls behind by one version. But generally, we want the new features. They're cool. They help us. So we keep updating.
All right. Thanks.
Correct me if I am wrong, but you are also the maintainer of CMSIS NN in Zephyr, correct?
Yes, I am.
And you didn't mention that here at all, yeah?
No, I didn't, because we're using CMSIS DSP. A funny story behind CMSIS Neural Network. We had a student that initially integrated that and got it working. I thought, oh yeah, sweet, we'll push it upstream. And then 6 months later, someone came around and said, oh, this system doesn't have a maintainer, so you contributed it, off you go. So we use the right tool for the job, not necessarily the one that I'm responsible for.
Okay, another question. So you are using basically the core, the Cortex M, whatever you have on this
M4, M33, yep.
As the device for doing all of the machine learning and the inference and so on, right? Yep. Would it actually help to have an accelerator or something dedicated to do this part, or is the Cortex M enough for you?
For this particular application, it wouldn't help. The execution time is not a big concern, as you sort of, like 20 milliseconds every 5 seconds may as well be nothing in terms of energy. The cost of spinning up a hardware accelerator is probably significant. Again, if you're looking at more complex algorithms, like anything image processing, I imagine would 100% benefit from hardware acceleration. But in this case where, even though 50 hertz isn't necessarily low, it's also not a lot of data, right? It's relatively easy to iterate over this. And like over time, the algorithms have improved as well. Like you might have noticed in one of my previous examples, it said 44 kilobytes of ROM, right? But this new algorithm with 2 kilobytes actually performs better. So over time, it's more efficient anyway.
So I think it's interesting that, I mean, you're able to get all of this information solely from an accelerometer, that what a cattle is doing. Is that right?
Yeah, that's correct.
Have you considered like any other, you know, sensor inputs to maybe refine that, or does it even matter, like microphone, heart rate, temperature, that kind of thing?
So I would say like more data is not necessarily always useful. So as I sort of mentioned with the gyroscopes, like we have the data there from the training sets, but when our machine learning guys looked at it, it doesn't really help the outputs. And then when you consider the fact that, okay, the goal is to get this running on an ear tag. The ear tag has a small battery, it's solar powered, and it needs to last forever. So these things run at sort of in the 0 to 100 microamps average current range, right? A 50 hertz accelerometer, the Bosch one we use, 10 microamps. 50 hertz gyro, 1.2 milliamps. Like it doesn't make sense for the application. And the fact that it doesn't really improve the performance just makes it even sort of worse. Same thing with microphone. Microphones, you're probably not going to get away with, if you use PDM mics, I think there's a couple of hundred microamps is sort of average. An actual like analog microphone is going to be milliamps. Like heart rate, it's a form factor thing. Like on the back of a neck, like it's got to be IP rated essentially. There's no real way to get like a heart rate sensor out of it. If you're on the ear, there's no real blood flow anyway to measure that. So the only sort of accelerometers are cheap. They are relatively reliable. They are super low power, and they provide a lot of information for the energy cost.
Makes sense.
So are you doing all of this on top of upstream Zephyr, or are you using the Nordic SDK for all of this?
So the main base is upstream Zephyr. For each release, we have our own branch with bug fixes and various functionality, which for whatever reason haven't upstreamed. But the base is standard Zephyr. Yep.
Okay.
Have you looked into using data that would be more like environmental data, like to the point of not using data that's not useful, like gyro, etc., but things like ambient temperature or like the actual environment of the cows?
So temperature is an interesting one because there's multiple kinds of temperature measurement. Environmental temperature for these sensors is not easy to get, and I don't believe it's that useful. And the reason why it's easy to get, it's not correct. So these things are sitting on the ears of cows. The ears of cows are sitting in the sun. It's totally reasonable to see a temperature of 60 degrees on the ear tag or in the collar, right? Like, sure, that's what the temperature of the PCB ends up being inside of it, but it's not necessarily related to the actual ambient temperature.
Yeah, and my point was trying to use maybe like weather forecast information kind of stuff and feed that into the algorithm as well. Like
So
maybe on the cloud, I guess, or like when you have.
So the challenge with that is for the ear tags in particular. So the collars have LTE connections. The collars themselves are Bluetooth and satellite. The satellite is uplink only. It's 9 bytes, and it's once every 6 hours. So there's no way to get that sort of information back down. I agree, in the collar case it could be used, but the collar is not the end goal. The ear tag is.
I was just wondering, is there room you see to improve as far as like the different type of behaviors that can be distinguished, or do you think this is a very good, like, accurate, you know, I guess data gathering? Are there, I guess what I'm asking is, are there other types of behaviors that in the future you would see as being useful to distinguish among?
Yeah, for sure. Even between the research collar and the ear tag, it actually outputs slightly different like categories, just because of the amount of data that we had to train the models on. It really comes down to how much data do you have to try and train these models on in the first place. Drinking is much less frequent than grazing, but it still happens every day. If you're looking to detect something like estrus detection for the cattle, for breeding purposes or whatever, that only happens sort of once a year sort of thing. So there's definitely more, and like this is just for the current state of the animal, right? Like there's plenty of other machine learning opportunities in terms of like disease detection, all that sort of stuff. It's just, can you gather the data to train the models in the first place? And yeah, do you have enough to differentiate between things which can look very similar? Yep.
Aren't there like spots where the drinking habit that you can identify by the location of where the cow is to say that it is drinking? There is no way it will be grazing at this spot.
Yep. So one of the cool things about this platform is that it does actually enable device-to-device communications. On the ear tag side, it's a bit too power hungry to listen on Bluetooth to hear, like, you could easily have a tag on the water trough which says, hey, I'm a water trough, and use that as a like, if it says you're drinking and you're not near a water trough, well then your algorithm is wrong, right? To use it as a feedback mechanism. Yeah, on the ear tags, their power, because like Bluetooth is relatively power hungry to listen for, so it doesn't quite work. But on the opposite side, you could easily have a device on the water trough which just listens all the time and goes, all right, sweet. This is the times all these devices were near me drinking, and use that as a annotation for the training framework. Yeah.
Couple of questions. The first one that's on all our minds probably is, does this make the steaks taste better? And
probably doesn't make the steaks taste better, but the guilty conscience, yeah.
So did you have to do anything special to get down to this low power numbers in Zephyr, or was it just already there for free?
So I'll use this opportunity to sprint my talk tomorrow, which is device power management, the journey to 5 microamps. But yeah, so over the last like 3 years, for example, since we started using Zephyr, the power management aspects of it have vastly improved. At the beginning, it was a lot of out-of-tree hacks and fixes to make this stuff run low power. These days, it's mostly an issue of driver support. Do the sensors you're using support the power management APIs? And basically, it's a question of, are you currently using it? If no, turn it off. So writing your application in a way that only runs the things when they're needed, and not just because you can, because in this case, you can't, because you'll go flat.
Right. Thank you for the presentation. I have one question around the training data set.
Yep.
You mentioned that you guys have been working on this project for around a decade. I'm wondering how much data, or how much can you share in terms of, like, I don't know, months of like data being recorded, which is classified, or something you had to gather to confidently iterate over and over your model?
So I think from like, there's, doesn't work properly, has it? There we go. Like this is like published research. You can, if you're interested in the particular details, you can go look at these links. From my understanding, the current model is sort of trained over somewhere between 8 and 15 data sets. So it is, even though trials have been running for over a very long period of time, over time you like change accelerometers and stuff, the parameters and how these things behave either improve or change. So you do need to sort of look at more at data that's relevant to your current platform. And the project has been running for like over a decade, and it's a process of continual improvement, state of the art. Like a decade ago, 100 microamps average power probably wasn't possible, right? We've got papers on the walls where ultra low power IoT node averages 15 milliamps. It's like, that's pretty funny now, right?
So I noticed the same sensors in the giraffes. Were there other animals other than cows and giraffes that you were able to use this device on?
Yep, so the ear tag, did I show this? Yep. So the ear tag itself is a commercial product. You can go to the website and buy it. It's not made by us, it's a commercial third party, like CSIRO is a research organization. But there's been people buying these to use them for a whole range of things, from giraffes, rhinos, koala bears in Australia. I think it was used on a couple. Phil, what else are the use cases? Cheetahs, lions, Ryan, yeah. Like wildlife researchers are used to spending a lot of money on hardware to sort of track these things. They're not necessarily cheap, but they are very cheap compared to some existing solutions. So, and the fact it doesn't need infrastructure as well, super handy in some situations. So yeah, many species.
And a small follow-up question as well, related to the grazing. Did you compare, and it's a little controversial, veal cows versus grazing cows, and the feed rate compared there?
Sorry,
veal cows, like cows raised more in place.
So most of the comparisons to date have been between breeds of cattle, as opposed to, Angus versus Brahman versus whatever, and also location. So as you might imagine, a cow grazing in Switzerland is exposed to quite a different environment than one grazing in the middle of outback Australia. That's been more what it's been focused on, as opposed to, the purpose, I guess, for which it's being raised. I guess from a high level of feed efficiency, this mostly matters when the cow is growing. So you want to optimize that process. Once it's reached its maximum size, that's probably the optimal time from a climate perspective.
So when we're just out of curiosity, so the farmers using those specifically for the cows, not for the wild animals, what do they do with this data exactly then after the data they get from those colors and those ear tags?
So in Australia, data from the collars they don't really get, because that's like internal research stuff. For the ear tags themselves, the initial sort of value proposition is that Australia has like ginormous farms. There's no infrastructure, and the sort of state of the art to finding your cows is when it's time to gather them together, you jump in a helicopter and fly around for 3 days, and you try and find your herd, right? If even like a handful of cows have these tags on them, they generally stay in a pack. You know to a relatively close approximation where most of the cows are. Makes it much more efficient to go and find them. I think the largest farm in Australia is about the size of like Denmark, right? So like, they're big.
That's location, right? I was talking more like what they're doing during the day, like the behavior ones. What can you do with that data that's useful?
So basically the conversion sort of goes from, okay, well, how long was the cow grazing for? Based on assumptions about where the cow is, how much grass has it eaten in that time. From that, you can sort of go, okay, well, it's ingested about this much. There's like a conversion factor to sort of go from that to like methane, for like greenhouse gas emissions.
Right.
It's becoming more important in terms of like food provenance as well. Like where are these things being kept? Well, not being kept, but where are they spending their time? And how intensive is the emissions they're producing?
All right, thanks.
All right, that's it.
Is that time, or is there's more questions?
Okay, can y'all hear me all right? Okay, let's go ahead and get started. Hey, so my name is Dan Grass. I work at NXP Semiconductors as a contributor and upstream maintainer to Zephyr, and this is a talk on a proposal for a way to do clock management in Zephyr RTOS. So we're going to first discuss kind of the current clock control framework. We're going to look at what you can do and, frankly, what I think is a pretty good implementation of clock control in its current form. From there, we're going to discuss requirements for a framework if we were to rework this clock control system, at least from my point of view. Obviously, at the end, I think we'll probably have time for discussion to mention other use cases I might not cover here. And then I'm going to go over a proposed implementation for this, and then some implementation details beyond that. I'm going to try and leave some time at the end for discussion, because hopefully there will be some. I know this is a problem we all have to solve, right? We all have clocks. So first, just an overview of what we have right now in the clock control framework. So this framework has been around since, as far as I know, this goes long before me and Zephyr, I think since the beginning. And it's based around the idea of hardware-specific subsystems. These subsystems are effectively an opaque pointer that you pass through from your clock consumer down to your clock driver. So what do we support? We support the ability to get a clock frequency as an integer. It's very straightforward, just getting the frequency in hertz. You can set a rate. It's worth noting that's also the opaque parameter, so there's no guarantees there. That's an integer. You can get the status of a clock. You can gate and enable it, optionally asynchronously. And then you can configure a clock via an opaque pointer, which is kind of a catch-all method of doing additional settings with clocks. Besides reading rates, though, all data is kind of driver-specific, so there's not as much enforcement here. Drivers can then also read clock settings from device tree to set up clocks at boot time. You'll see this being done a lot for root clock sources, things like PLLs being read from some sort of device tree configuration. And then if you want to, again, the configure API is kind of a catch-all. You can shim a lot of stuff in here to accomplish a lot of different configurations with clocks right now. So now let's look at a usage example. I wanted to highlight ST here. I work for NXP, but I'll be frank, I think ST did a good job. The clock drivers, well done. There's a lot of functionality here. There's, and Erwin, correct me if I say something wrong, or make a face at me if I say something wrong, but there are SoC-specific clock drivers that implement functionality for each, as far as I can tell, series, and then there's these macros. So STM32GT clocks, what does that do? It sets up configuration data for the clock based off what's present in the device tree, based off these specifiers. So you have this clock node in the device tree, and then these specifiers, and this macro extracts that data, packages it up in a way that the STM clock driver will understand, and then you can pass it through with this clock configure API. So we have the ability to do things like enable or configure clocks, and that is all device-specific data. Things like register offsets and bits are being encoded by this macro. Beyond that, the implementation that ST has lets you do things like multiplexer selections. There's this driver for clock mux compatible that can apply selections at boot time for clock muxes. So you've got access to muxes here. The root clocks, things like PLLs, can be set up from device tree properties on the reset and clock controller node that ST has. So effectively here, you've got the ability to configure your root clocks. You've got the ability to configure your muxes. You can gate and negate. There's a lot available here, to be frank. But what isn't here, and what do we have issues with? So one thing here is code reuse. Fundamentally, things like dividers and multiplexers are going to get reused across SoCs. Things like PLLs, not so much. PLLs are IP that's going to change when you change your process node, things like that, and you can't always reuse them. They may have vendor-specific features on each implementation, but dividers and multiplexers, they divide, they multiply. There's not that many ways to do it, and they're going to get reused. We should reuse them. Additionally, runtime clock configuration is kind of limited with what we have now. You have the ability to gate, ungate, But more complicated stuff like PLLs, again, there's that configure API, but at some point, there's problems. If you're trying to pack an entire PLL configuration into that pointer, and you have one function implementation to do it with for your entire clock driver, you can run into issues, especially with optimization, if you have a big switch statement or something like that to handle all that code. There's also not really anything for callbacks. It's worth noting there is, on and off callbacks, but there's no callback for, hey, someone else just reconfigured a root clock, that affects you. So if you're a consumer, you're not aware if somebody touches a clock that you're interested in, or rather a root clock that you're interested in because you are a descendant of that clock. Your node is that you're interested in. Additionally, clock control framework, it leaks device-specific data. So right, ST has this macro, this ST DT clocks macro, which works well for their drivers. And theoretically, we could all do that. We could all have our macro that does this, but what about designware drivers? Those aren't vendor specific. And there's also the fact that even if we did do a totally generic macro, you're still looking at issues like clock callbacks not being available in the framework right now. Additionally, the set rate API, I'll be honest, I kind of have a bone to pick with this one on embedded devices. We'll go into the proposal later, but not everybody wants the overhead of saying, give me clock frequency X and figure out how best to do it. That's an expensive operation to do on a low power device. And currently we have that opaque pointer for it, but that just introduces new problems because we're leaking device-specific driver, to be clear, clock driver-specific data out into consumers. So now let's talk about the requirements if we're going to rework clock control and try to implement something new and a little bit more capable. So just an overview of kind of the clock hardware that we all have and love. And this is the only photo I believe I have in the entire presentation because graphics are hard to find for clocks. So I apologize. It's dense. This is just part of the clock tree of one of the LPC series SoCs. So you have gates, often per peripheral. Additionally, you can sometimes gate root clock sources. And then sources themselves, you can sometimes power them off at runtime to save power. Beyond that, you have kind of dividers and multipliers, very standard, just divide a clock, multiply it. And you have multiplexers, so the ability to select from a different set of sources to then clock a given output. PLLs are also worth highlighting here because a lot of the stuff that I just mentioned is kind of generic. Sources, there's a gate bit or something like that. Dividers, again, there's only so many ways you can divide a clock. Multiplexers, it's usually just a setting and a register that corresponds to each input. But PLLs can have all these different settings. They're very much specific to each vendor. And as I mentioned earlier with code reuse, that's something that's a challenge for clock control drivers is how do you effectively do code reuse if you have a basically SoC-specific PLL in every SoC. Additionally, PLLs are something that kind of brings us into power usage because if you really want good power consumption, you've got to power down things like PLLs for low power modes. So then framework goals. First and foremost, we need feature parity with clock control. This is an API that's been around since 1.0. We can't just tell developers, hey, sorry, we're getting rid of this functionality that you needed for your application. We need to have a path forwards for them. Beyond that, we want the ability to configure clock settings at runtime. We want the ability to, say, transition from a high power set of clocks to a low power set of clocks and support powering off clock sources, saying this PLL is no longer used, we're going to turn it off, things like that. We want the ability to notify clock consumers when a parent changes rate. So we want, for example, if you have a clock tree with a PLL at the root and you change your PLL's output frequency, we want to be able to propagate a notification down to consumers saying the rate has changed, adapt to that. We also would like to describe clock hierarchy and device tree. I'll get to why I feel this is useful later and the implementation benefit it brings us, but initially I think the value here is that it makes it much easier to understand what's going on if you have things in device tree, if you have nodes for different clocks. From there, we want to maximize code reuse. So I mentioned earlier, digital IP, stuff like that, things that are not going to be reworked for every SoC. We want to be able to reuse that even if we need a custom driver for each PLL. And we want to minimize flash and RAM footprint. This one is really important to me because this isn't something that is optional. clocks are always on your SoC. If you're using your SoC, you're clocking it. So I mentioned earlier the set rate API. I think we probably should have runtime rate calculation be optional. I think that we need a way to deal with this that doesn't explicitly require you to have a large flash footprint to calculate a given rate, to request 12 megahertz, and then have your clock framework figure out what that is. Linux can do that. I frankly don't think we should make that a required feature for every implementation. I think that should be something you can turn on if you don't care about the power consumption and or you want more portability, but I think it should be possible to optimize in the direction. So now let's get into the proposal and how I think we can go about implementing something like this. So first off, just kind of a broad overview of the way I think we could go about this. So I think we can do 2 layers here. So there's first off this clock driver layer. And the idea of the clock driver layer, it's very loosely based on the idea of the common clock framework, which, if you're not familiar, exposes clocks as a kind of object and has fields with different APIs you can call on that clock. And the clocks have their hardware-specific data that's relevant to only them that they use to implement those APIs, things like getting the clock frequency, setting the clock frequency, stuff like that. Clock objects will then also hold references to their parent, which is needed because if you are describing each clock element, and here I mean when I say elements, things like multiplexers, dividers, each of those would be an element. It needs to know what its parent is, to ask its parent what its rate is, and it needs to know what its children are to notify them if there's a reconfiguration event, if the frequency is changing, and it needs to pass that notification downwards. So all of this is good, and this is a way of doing clock drivers, but then there's a management layer. Why does this exist? So this exists because we don't want set rate. We don't want the ability to request a rate to be something that is mandatory, but fundamentally, we need a way to hide driver-specific data from consumers. Consumers shouldn't know which SoC they're running on as far as clocks go. They should be willing to, or a driver should be capable of working across a wide line of SoCs without any knowledge of the underlying clock framework. So the idea that I think we can go with here is kind of similar to pin control, where clock configurations get abstracted to states. There's a high power state, a low power state. And each state has a series of clock nodes that have hardware-specific configuration data as specifiers. So by doing this, you can set up your multipliers and dividers and everything in these states, and then the consumer simply requests, run state, sleep state, and the device tree is where we describe what that actually means. Clock outputs, I think we should still allow them to have their frequency queried directly. That's not something that is nearly as much overhead to implement, and it is a relatively straightforward thing. Everyone needs to know their clock frequency in hertz. Beyond that, this concept of output clock nodes. So we still want the ability to set rate, and I'll describe these more later, but the idea of the output clock node is that we have this hardware-specific specifier data on each clock node, but the output clock node would have a frequency, and that would be your way of saying, I want a frequency rather than a configuration value. And then beyond that, the clock management layer would support rate change callback, so consumers can register for a notification if there's a rate change. So now let's start looking at kind of a little bit of code. So this is the kind of clock driver API that I think we should use. These APIs are things that would only be available within the clock driver layer. So if you remember from the prior slide, there's this management layer and this driver layer. Drivers are all of these individual clock nodes. So clock drivers will use this API to eventually inform the clock management layer about things like the rate that they're running at. So for example, a div might implement get rate by requesting its parent rate and then looking at its register settings to figure out what the output rate of that div is and then return that value. So you have a description here. Notify is kind of our call down from a parent. So notify is how we pass a notification from a parent to a child saying there's a reconfiguration occurring, you need to deal with it. And you can see that parent rate parameter, that's how we pass down the new rate of the parent. This is kind of like clock recalc rate. If you've looked at the common clock framework before, it's an idea of the parent has changed rate, now the child needs to recalculate its rate, and that will be passed on down through the tree to the leaf nodes that are peripherals generally. Get rate is what it sounds like, reading a clock rate in hertz. Configure, I'll go into what this data is more later, but this is kind of how we actually set a clock's configuration and configure a mux to have a given selection or something like that. Set rate and round rate, these are intended to be optional APIs. So the idea with both of these is that these are the way we handle users who want the ability to request a given frequency for whatever reason. Set rate is what it sounds like, set a rate in hertz. Round rate is relevant because if we're implementing set rate, it's useful to be able to request from a clock node, for the case of like a multiplexer, what that clock node can actually support. So it's useful to ask a clock node, this is the frequency that I'm looking for, what's the closest to that you can actually provide me, so the multiplexer can make the right selection when it's trying to implement that functionality. It's also worth noting that within this, because we have each clock node being represented by a clock structure, that things like external clock generators could be supported with this, since there's no explicit requirement that the clock implementation, that is, the struct clock, be describing something that's on the die versus an off die FPGA or something generating a clock that is then going to get used by the SoC. So then the clock management API. I mentioned this idea of states previously. It's also worth noting that you can have a driver define custom states, because we kind of are going to by default likely define like a run and idle state, but there's more than likely cases, just like pin control, where there's additional states a driver needs to deal with. Beyond this, you can register for notifications, and the idea here, you saw that notify API. We'll go into implementation a little bit later of how this would work, but essentially the clock management API would deal with these notification callbacks as well and forward them out to consumers. Now the API itself that consumers actually see access to, not the clock nodes, but the consumers themselves, is these three APIs. So apply state is kind of our analogous to pin control, where you apply a given clock state, set callback, registers a callback, get rate, gets your rate and frequency. One thing that's worth noting here that I'm open to feedback if we want to try and find a way to support this, but there's no support for explicit runtime rate setting with this. The reason why is because if we explicitly support runtime rate setting, then we're going to have drivers that start to require that. And if that's something we need, we could look at like a Kconfig to enforce that requirement or something like that. But in the initial kind of look, I feel like the value of this is that for smaller devices where you want to scale down, or larger devices where you want to scale up, we're not going to end up with a driver that tries to cross that entire range of devices, but somewhere in there says, I want to calculate the frequency I'll need at runtime and then request it, because if you do that, then you've automatically pulled in all of these set rate functionalities that have higher flash impact. So from here, let's start looking at kind of how this device tree would be defined. So the idea here is that we define each node of this clock tree hierarchically. So right here, we're looking at part of the clock tree of an LPC part. There's a clock multiplexer and then a multiplier down here. And the idea here is, the multiplier is the child of the multiplexer and can request a rate from it. So the reason we're doing this all hierarchically in device tree is because then we can build that relationship of clocks, clock structures, that reference their parents with device tree macros and then can query rate from their parent. And we can, the other way around, have parents notify their children of reconfiguration because this hierarchy is already described for us. So beyond that, let's look at the device tree definition here. So states being defined in device tree, I've mentioned this previously, these kind of specifiers. And what do these actually mean? So these are all hardware specific. That's kind of how we hide, I guess, the hardware specific details. We put them into device tree here. And in this case, right, this was a multiplexer and a multiplier. So the multiplexer right there, that 0, that's in this implementation just a register setting. That's selecting a given input. And then that multiplier value is just, for this specific multiplier, that means pass it through unmodified. But those are all device specific. The idea of this output node I mentioned earlier is sometimes you don't want to go to this level of detail with your SoC, you just want to request a frequency. And going back to this slide, an output node would probably be defined as a child of this multiplier, and it would be responsible for taking in that specifier and dealing with it via the set rate API, so that you wouldn't have to do each individual configuration like this. But the value there is that you have a choice. You have a choice between, okay, I'm willing to accept the flash impacts, I will use this given rate value, versus I want to drill down, save flash, and I'm going to configure each multiplexer and each part of my clock tree individually. And then it's also worth noting, nodes can define additional states if needed beyond just this default and sleep configuration. So now I wanted to look at kind of how we would migrate here and kind of check in to see what is supported and if there's anything we're missing. So clock control get rate, that's a given. We have support for that. It's basically a one-to-one mapping. Set rate, this is one of those. This is something I'm expecting feedback on, to be frank, and I'm interested to discuss how we could deal with this more effectively, because for higher power devices, there may be a need for them to determine what frequency they need at runtime and then request that frequency at runtime. Right now, with this proposal, the way they would do it is they would all have that in device tree, and there's not a way for them to explicitly request that frequency at runtime. So they would use these clock output nodes. Clock control configure is relatively straightforward. This was already kind of passing a void pointer through, and now we would use clock states to define those configuration values and then pass them through to clock drivers. Get status and async on. So both of these, I think we can probably handle via the callbacks, because what you're interested in is the status of your clock, and we can pass that down via this notify API, in particular async on. If you're looking to see when a clock turned on, then you can call this, you can wait for a callback to say its rate has gone from 0 to not 0, the clock is now on. Clock control on and off both, I think, can be dealt with via these clock states. This idea of now a gate is described as a clock node with a 1 or a 0 to say this is going to be on or this is going to be off in this configuration. So now let's look a little bit at how the framework would be implemented and what that would look like. So I wanted to just quickly walk through how these nodes would be implemented to give you an idea of the implementation for one of these node drivers. So this is for a divider, and the way this works is relatively simple. It requests the rate from its parent node. It looks at the divider setting in a register, and then it divides and returns that value, looking at configure. So configure is kind of the meteor API here. This void pointer, I've kind of been dancing around it. Where this comes from is that specifier value. So that specifier value on the node gets passed into this function when you go to apply a state. So jumping back a few slides real quick just to try and link this up, that specifier value, that 0 is what gets passed into configure. And then you take that value, cast it to what your driver knows it is, and you apply it. So this allows you to deal with, a divider, obviously that's probably one value. A PLL is going to have more than one specifier. There's going to be quite a few specifiers to configure something like that. And then this clock notify children call. So what that is notifying children of the clock reconfiguration is about to occur. And this is necessary because say you're dealing with something like a flash, SOC flash where you have wait states. It needs to deal with and increase the number of wait states prior to the clock frequency rising. So this notification will occur before settings get applied so that any consumer can deal with a rate change before there'd be a crash from the clock frequency increasing or something like that. And then notify. So notify is generally a simple implementation. You take in your parent rate, looks a lot like, honestly, the get rate implementation. You take in your parent rate, you calculate the new rate, you pass that on down. And this is worth being noted. This would be called from the parent clock, and we propagating downwards. So now how do we implement the subsystem? So I mentioned in the last slide how we're going to pass these values through, these specifiers through. These macros are what we use to actually extract those values. So these kind of look like what you see in pen control. The big difference here is we use the compatible to determine what the macro name will be, and then your SOC, or if you have an external clock producer, you'd have to provide a header file with these macros in it, but you would provide these macros, and then the clock framework uses those macros to extract what the configuration values it needs to pass through would be. And then we configure set points with this clock configure API. So, I've mentioned the concept of the output clock node with this frequency before. That one is kind of the oddball case, but the way that would be done, right, is that you take your given configuration setting, which in this case is just a frequency, and instead of configuring some multiplexer register value or anything like that, you just call the clock set rate API on the parent clock, and that's how you apply your given frequency. From there, how do we implement clock callbacks? So I said there's kind of these two layers. What I think we can do is we can define kind of a minimal clock structure for the consumer node, whether that be a UART, an I2C, whatever peripheral it is, and that clock structure implements the same notify API as all the other clock structures, right? So the infrastructure is the exact same, but that callback, as it goes down, the handler for the notify API at that level just forwards the callback to the consumer. So that's how you hook that in. So now I kind of wanted to go over the current status of this implementation. So I have a basic implementation completed for the 55S69, which is why I keep referencing its clock tree all over this presentation. We can configure the clock tree to run a basic Hello World application. The main issue I am still trying to figure out is flash. So currently, it's about 1 kilobyte of additional flash to do this framework with the notification callbacks. If we turned that off, because for a case where you don't care about power management, you're likely setting up clocks once, we get it down to about 300K of additional flash versus using the clock control framework, but there still is a flash impact. RAM in both cases is negligible. I think less than, I think it's less than 100 bytes, but it's significantly less impact. Beyond that, there will be an RFC for this. I just need to complete the set rate and rounding implementation to validate that they can actually function and then put documentation together. I also wanted to cover a couple of alternative options before I open it up to questions. One thing I explored for this was using this concept of these set point and states in an SOC-specific manner, so something like very adjacent to pen control, where there is one singleton driver that handles the clock state application, and that's what you have for your SOC. One big problem with this is you can't have off-chip clock producers. Another issue with this is your code reuse is pretty minimal. But there is an RFC for that approach if you'd like to look at how that was done. We could also implement this using the current clock control subsystem, The main concern I have for this is if we want to do that child-to-parent reference, which I was describing earlier, which I think is crucial to actually generate these callbacks. Device structs are kind of big, y'all. Like, compared to this clock structure, which is 3 pointers, if you have like 25 clocks in your tree, which for the basic Hello World example, I do, it's like 100 bytes per, it's a lot of flash. So that's why I think we probably need something different here, because when you have this many nodes, it gets expensive. Additionally, there's the concept of the set rate API, which I am still of the opinion that we should probably try to avoid requiring that for every base image, because smaller parts just don't need to calculate their entire clock tree at runtime like that. And then beyond that, every extra API field, you'll notice there's not that many APIs in the clock driver implementation. That's because those also add to flash usage. And then there's no facility for rate change callbacks. So that concludes the presentation. We've got about 10 minutes for questions, which is a little less than I intended, I'm sorry. But yeah, who would like to go first? The anticipation is killing the bricks. Sure.
Oh, hello.
Oh, or that.
Thank you for your presentation here. Did you consider the use case of like in power management, where you can actually say this device is busy? So if you have ongoing transactions, for instance,
We can't change the clock right now, please don't.
Please
yeah,
don't.
So this is, I mean, I have thought about this. I want to give credit to Erwin, because I talked to him about this a couple days ago, and he asked me that, and then I thought. But I didn't screw with the slides because I'd already uploaded them. So I think we could do this via the Notify API. My idea is, right, we're propagating down to children, and there's a return code. We could make the return code say, hey, I'm busy, and then that just propagates all the way up. Because you call this Notify Children, jumping back many slides, you call this here. If that returned an error code, you just wouldn't apply, right? Something like that. Another thing which I assume someone will ask about, because I've been trying to figure it out too, is the idea of how to deal with a situation where you have just changed your mux to select a different source, and now you no longer need that PLL you were previously very interested in. This one I'm not sure on, I will be honest. My best idea right now is to also use the return code of Notify Children and look at that. But the problem with that is that if you reconfigure, you have to then do another configuration call on your PLL to find out that you aren't using the child. You're raising your hand. Do you have a better idea? Because I'm interested.
So I was thinking about that exact thing. I previously did a power management system for Kinetis, which I think you know well, and the complexities of it. And in that case, what we were doing is we're basically putting a ref count.
Yes.
And so by using a ref count, say on the PLL, on at the different, I don't know if it's at the different points of the mux, or
using a ref count,
something along those lines.
No, I think a ref count, I mean, I'll be honest, I'd like to use a ref count too. The reason I didn't go with it right now, there's a few. One is that, again, Flash, if you add an API to tell the parent, decrease your ref count, you've just added an API for everything. The other thing is actually, again, cursed Flash optimizations, there's no, let me see if I have a backup slide with the struct clock in it. I've turned this off, that was a not wise choice. Okay, there's no backup slide. That's fine. The clock structure, as it stands, only has one pointer to a device-specific hardware data, because usually you only need ROM data for like a mux or a div, and you only really need RAM data for something like a PLL.
So there's kind of that problem that if you start putting a ref count and everything, yeah, I mean, that is something I'm aware of. The other thing I've thought about for this is something like using maybe a power management like framework to do it. But again, you have the problem of anything more in this clock structure is additional flash. Yeah, I'm still trying to figure out the best way to do it. It's worth noting if you're willing to use this method where you explicitly reference each device in your set points, then it's very easy. You just say, oh, my PLL doesn't need to be on anymore. Please turn it off. But that doesn't solve everyone's use case, right? That doesn't solve the use case where you just want to request a given frequency.
It also doesn't solve the problem of you want to be able to drop to, say, a different low power state. Like, again, with the Kinetis, all the different low, you can only go to this low power state if these peripherals are off.
Yes, yeah, there's transitions.
It ties into clocks and other things, but that it doesn't play well into that either. So.
Yeah.
Did you consider so we were talking about device frequencies here. Did you consider to extend, or will it allow to play with core frequency as well, to do some frequency scaling, to enable frequency scaling?
To enable like dynamic frequency scaling or something like that? I think, yeah, yeah, because then you have, I mean, with this, you could accomplish that provided you knew what your target frequencies were at runtime, because you could set them with these clock output nodes. But no, I haven't dove into it that deeply. I think it superficially probably would be something you could do with this.
Because one of the issues in frequency scaling is that you have to inform everyone that your bus clocks have changed. So
yes, yeah, and
so
that's
this
what these,
you're adding a part of you're solving a part of this issue. It would be interesting to see what are the missing bits to enable the frequency scaling.
Sure, yeah. I mean, you should, with this framework, if you request a new frequency for your core clock and you have to change muxes to achieve that or something, notifications will propagate down. So other consumers would be aware that their bus clock has changed or something like that, because they'd each be subscribed to a notification for it. But yeah, no, I mean, if we did something like this, it would be interesting to see what comes out of it. And I want to be clear, it should be obvious at this point, I don't have all the answers, right? This has to be a group effort to figure out what we can do.
On one other point that we discussed is that maybe, so at one point you are quite close to power domain here.
Yes,
so maybe it would be interesting to see
if we could use a power domain here. Yeah,
yes,
no, that was something I was thinking about as well after you mentioned it. I mean, potentially, the thing that I think we really need to figure out is how we can. The main thing I still don't have a great answer for is the question you asked, like how do we deal with a situation where we want to power down a root node because it's no longer used. Because a ref count is obviously the simplest solution, but are we okay with the flash impact of an additional API to say I'm no longer using this, and then yet another thing in the RAM to track that ref count for each node? Yeah, and that's an open question. We may very well be, right? So, yeah.
But anyway, it's quite interesting, quite good progress. Thank you.
Absolutely.
So, I mean, there was being able to describe everything in device tree. Were you able to, at build time, basically validate that your clock tree, description was valid for because right? I mean, you go and like.
And that's a very good question, a good concern. No, I don't have. Currently, there's not. The validation that could be done would be something where your PLL, when you go to request a frequency or something like that, would say, no, this isn't something I can support. And that would be relatively easy to implement, but we couldn't do it at build time. I'll be honest, I think part of the way to do this at build time is to offload that type of clock configuration to some type of solver, right? I'm not sure what that looks like, but for embedded devices, often the way that you configure, like, I mean, I know Linux supplies something like this, where you say, here's my clock tree, here's what I want it to look like, spit out C code. I think we probably want solvers that look similar enough to that, to do that kind of setting up muxes and configuration and validating that at I guess, before even compile time. Yeah. Are we out of time?
Yep.
Okay. Well, if anyone wants to talk in the hall, I'll be available.
All right, I think we can get started. Full disclaimer, I hope many of you know that, but it's a talk, it's in the schedule, but it's actually slightly different than the regular talk. It's a birds of a feather session. So thank you, ChatGPT or whatever, for the weird-ish image. I have a few slides, a few sort of things on my mind that I will throw at you, but I hope this will be more of a conversation. All of you are Zephyr people, or are there people more from the rest of the conference? Because I'm actually interested in the latter, if there are any people. Because it's also about sort of exchanging, and you might be involved in other projects, open source projects, or anything really. Basically talking about all things documentation. Are there things that other projects do that we could get some inspiration from? And obviously, like what is missing potentially in Zephyr? There was a BOF last year at ZDS 2023 in Prague, documentation BOF, where some topics were discussed. I want to sort of give a quick update on some of the things that were achieved or accomplished by the project since then. And again, this is, I mean, maybe not for you in the room, but some people might end up stumbling upon the recording of the session or the slides and might find some of the things that we implemented to be useful for their own projects. So there's that. And then, yeah, open discussion. And thank you, Anas, for advertising the talk on our WhatsApp. Hopefully more Zephyr people will join to discuss what they think we could be doing better, we could be doing more of. What are some of the things that make your lives, maybe as contributors, maintainers, too difficult? Like maybe some of the documentation tooling or whatever is painful. We should certainly discuss that. But yeah, some of the things over the past few surveys, and if you look on Discord or if you talk to people at conferences and whatnot, some of the complaints in the past around Zephyr and its documentation have been around the fact that it's hard to navigate the documentation. Things like I'm navigating the documentation of a particular subsystem. It's kind of hard to find specific samples for this subsystem. Similarly, like what are, for a particular board, what are some of the, like what are the drivers and the peripherals that are supported? We lack some of that, so there have been some improvement in that regard. And another complaint was the search is useless, basically. So quick update on both fronts. In terms of navigability, we are leveraging the fact that our documentation framework / engine, Sphinx, is actually quite extensible. So there's dedicated annotations that one can use. And if you're interested in contributing new code samples or maintaining some code area for which this hasn't been adopted just yet, please have a look. Effectively, it allows to add just enough metadata to the header of a sample's documentation README, so that not only we have a consistent way to sort of describe, give a name and a description to each and every sample, but also a way to indicate what is or what are the relevant APIs that this sample basically is a good demonstration of. And so you probably didn't know or didn't remember that there is actually a PS2 driver and PS2 support in Zephyr. And so the one sample that we have is effectively referencing the API, like the deoxygen identifier of the API group for PS2, which means that to the point of navigability, should you stumble upon the PS2 overview and like reference API reference page, you have the blue box thingy that lists all the samples that are applicable. Not a big deal to some extent, but that's I mean, people seem to like it. We will talk a bit more about maybe how we could do things even better in terms of sort of standardizing the way we document subsystems to surface even more information. I think it would be useful, like similarly to the way there's now this ability to quickly know about samples that are relevant. There is this one thing that you can actually see here where whoever authored this page many, many years ago, I'm sure, they did, and I think that was the right thing to do, they thought it would be useful for people to know what's the name of the main Kconfig that turns the subsystem and the functionality on or off, except that we have no standard way to do that. So it's up to the maintainers to think about listing those kind of options. Maybe we can build some kind of infrastructure to make it more mandatory and more systematic, that people would list those kind of things. Similarly, I think, and kind of digging into the rest of the conversation for later, but I think it might be useful to surface better what are some of the dependencies, at least at a really, really high level, of a particular subsystem. We hear a lot, and again, back to developer surveys and just like general feedback people make on Reddit and whatnot, like Zephyr is bloated, for the lack of a better word. Like Zephyr is like too many layers of dependencies, blah, blah, blah. It could help if, I think, if for each subsystem or each piece of functionality, we would give a sense of what it is you're pulling, if anything, when you're enabling the functionality. NVS, like you want to use non-volatile storage, like what is the overhead? Not necessarily in terms of like actual footprint, but more in terms of giving a sense of whether you're going to need to enable crypto as a mandatory feature. If yes, then well, maybe you don't want to use the functionality, or you want to reconsider it. Yeah, so well, that's kind of a digression. We can talk more about that. Let's finish it up with some of the things that were added. People were complaining about the search. So what we had at our disposal with Sphinx, which we still do, is not necessarily the best at ranking the results. So one thing we did late 2023 was to add support for Google programmable search. So basically embedding Google with our own look and feel and our own style in the documentation itself, so that people can search faster and more accurately. It's still sort of opt-out, I guess I should say. Like people can still use the old system if they want to. But yeah, that's a feature that the project is actually funding. It's maybe a couple $100 a month, or something like that, to be transparent here. So that's the stats. During the weekdays, there's 1,000, 2,000 kind of queries that are being performed. As an FYI, just like last year, I don't know if you remember, I was also sharing those metrics. I mean, take them for what it's worth, but it's kind of interesting that the vast majority of the kind of information that people are looking for is what you would call basic, I guess, to some extent. ESP32 ranking 4th is also an interesting factoid when it comes to the popularity of this particular platform. But yeah, and that's actually interesting also to have. I mean, we now have access to those kind of statistics, and so GPIO, top query, top search term, sort of. If you try and search for GPIO using the old system, not even the top 3 results were really useful. Now it's kind of better because you get the real thing as the first result. Sure, we could have fixed probably maybe the Sphinx thing and build our own search engine infrastructure, but that's not what we do, I think. So we'd rather use what's available out there. With that, I hope we can sort of open it up for discussion. Some of the things that, as a documentation manager or co-manager, some of the things that come to mind in no particular order, and I might have forgotten important things, but in general, I find myself spending a lot of time. It feels like I'm nitpicking, frankly, when I'm doing this kind of feedback, so that's why I want to discuss it, but making sure that our documentation is consistent is kind of tricky. We might be missing some guidelines, but I wonder if we want to look at some tools. I was playing with a tool the other day, with like one thing that I found as both a consumer of documentation or a maintainer that reviews new documentation. Sometimes you would have a fairly long and like legacy-ish documentation page which people keep adding to. It kind of shows when people just add stuff that they write in their own tone, they don't necessarily think about making sure that it fits with the rest of what was already there, right? Like I don't remember exactly what kind of PR or what kind of ARIA it was the other day, but someone was literally adding a bullet point to a list that was talking to the developer in the third tense, and whatever they added was doing it like differently. And it was like, you can, and then the fourth bullet point was doing it differently. I mean, maybe I'm that kind of OCD sort of like thingy, but I think you get my point. Maybe we can have some either better guidelines of tooling, so I don't know what people think around that. Similarly, or I mean not similarly, but do we want to do things differently when it comes to all things images? We keep obviously getting more and more in the tree. Sometimes they are either too big, or we're ending up getting new diagrams that we cannot really make edits later on because people just submit a fancy diagram that they created with whatever tool, and then that can become a challenge. And then there's this discussion around subsystem templating. I don't know, like, is that a good starting point? Are there other even more important topics that people have on their minds and they want to provide feedback on? Because like, if it's going to be a monologue, we can all go and have drinks anyways, probably. So, thoughts? Yes, please. To read. Yep. Yep. Bricks. But and the reference as in like the top level URL or something more specific? I guess. Yeah. And is there a pattern of like some particular areas where questions keep coming and coming? Okay. Yes.
So new to Zephyr-ish, maybe about a year or so, kind of off and on. And heard talk about iterable sections, which was like new to me, right? So like, I got the documentation right here. This page contains a reference documentation for iterable section APIs, really, which can be used for defining iterable areas of equally sized data structures that can be iterated on using struct section for each. And it tells you usage, and then it goes a couple things there, and then it goes API reference. And so it's like, to me, I'm like, okay, I still don't know the rationale, right? Like,
yep.
like there's a lot of holes in there's some areas where it's like really good, and it digs into, okay, why this kind of thing exists. But there's other things like this that are like, okay, why would I, like I can see the code, but like, why would I?
Yeah, it feels like someone wrote the documentation because they were asked to, and.
There's a lot of detail, but like when you make it when you're defining something and you use iterable,
Yeah.
iterable, right, and you're not using other words to describe that, or you're not saying, you know, the rationale of why this would be, useful. You're just kind of getting into it from a perspective of like, I already know how to use this, so I'm going to write a doc page on it. But if you're trying to use it like as a kind of a tutorial, explain to people why this exists in Zephyr, then I think that's one of the pieces that could be integrated into more of a, the rationale. Their comment early on one of the first talks is there's a lot of detail in documentation, but sometimes there's not a lot of guidance.
Yep.
So there is actually, this is like part of the journey. You go like 1 minute out and start looking at other
Yeah. Concepts should be a mandatory thing. Yeah. Yeah. But you don't know why. That's default is Google. If you browse the latest documentation, if you browse a say 3.6, it would default to the built-in because when you browse an old version of the docs.
Yeah, I think I've had it where I've gone back to the older documentation and still switches back to the thing. Okay.
Yes, that should be the behavior. Yeah, come on. Oh, right, yes. Yeah, because I was going to say, yeah, it's there, but no, you're saying something different. Not reporting an issue, but rather acknowledging that you...
Yeah, right. So then at least there's an identification that says, hey, somebody, we can take a look at this thing that, hey, we've got 60 downvotes.
Yeah, or 0, which is also an indicator of nobody ever found it, ever. Yep, I don't know, like there's the whole maybe GDPR and whatever info we might need for that, but yeah, I like that actually. Yes? Is somebody take notes? Is somebody taking notes? I mean, it's recorded, I guess. Yes. Yeah. Good. More. Yes, please.
Just wonder about like when sometimes there may be some inconsistency or the system is lacking some details in page. There could be a more direct link to like who to ask, the developer or something about that feature, or have it flag something as okay, this part needs some improvement. Because not everyone might like.
Yep. Yeah, mapping the pages to the sort of the area they belong to. Yeah. The question is when in a so tell me if I'm wrong or if I when a particular area seems like it could something's wrong with it or like could use some improvement. Who should I reach out to, or like is there like a Discord channel or a like is that what you kind of? So that, I think there kind of is. On a particular page, if you see something wrong with it, you can directly, like the usual problem, you can directly open an issue about it. So it sort of like gives you already sort of a direct link to open an issue, which might or might not be a good idea because you're going to effectively open a ticket, whereas maybe you just had a question. So yeah, I guess what you're saying is maybe something else could be done to. Yeah, but the point is that it might not be exactly an actual problem. It's more like something that's unclear. So yeah, I don't know. I don't think I have a good answer. Yeah. Yes. Yeah, but just being like meh, meh, it wasn't great. Yeah. Yeah, I know. That's like, yeah, you know that is generally wrong. Yeah, yeah. And yeah, getting started might be a really good candidate for really bad ranking. Well, yeah, there are. We don't have the best infrastructure to pull those numbers and to exclude bots, etc. I remember doing that in the past. Well, I can tell that, for example, the PDF nobody looks at because it's often broken and nobody seems to. The PDF, like it's a page among others, I guess. But yeah, there might be. Yeah, the stats. I think we were talking about it with Stefanos and Fabio at some point. Like, we would require some kind of infra to run proper stats and like GDPR compliant stats, but maybe we need that, yeah. Yeah, well, actually, so that briefly, and I know there's many raised hands. Briefly, Keith was telling me the other day, and it might be related, for each page or like subsystem documentation, having some related resources, links, including like, here's a really good ZDS talk from Marty from 2 years ago about device 3. Here's an awesome, like, if you love semaphores, like, look at, right. And yeah, exactly. And so those in like related resources would be relevant Discord channel for the. Well, I mean, we wouldn't be creating new ones. Like, I think that's the. Yep. Yeah. Yep. If you guys don't mind using the mic, I know that
sure.
it's not necessarily the best setup, but we have people recording, and just for accessibility, really good. Thanks.
Yeah, I'm just intrigued to hear more about your thinking around sort of like maybe developing a bot or something like that that can actually ingest both your Discord feeds as well as your documentation. Because I've noticed that like a lot of companies are starting to have bots that are trained specifically on your own, on your own documentation and data set. And they're actually like pretty impressive with what they can do. So people can come in and that could field a lot of like easy discussions.
So you mean chatbots? Like something that would provide suggested answers sort of stuff?
Yeah. So like if you have a question about I2C, the chat bot would actually probably go, well, here's the pointer to the documentation. Here's a bit of example code.
Yeah, it's like the let me Google that for you thing, but more.
Yeah.
Yeah,
I'm just saying that a lot of companies are sort of heading that way with having that as the interface to documentation as opposed to
I know.
that
You're right.
mechanism.
I think users coming to Discord, they're not looking for a bot. They're looking for somebody to chat with about a given subject. So feeding them to a chatbot and nobody then responds because, well, the chatbot already responded. I think that will actually be a worse service than what we have today.
And I think this is digressing. It's not this topic here. This talk is not about how do we help the community. It's about how we improve the documentation. We really need. I mean, we can have bots and so on, but at the end of the day, the documentation as we have it is really the source. And how we, I mean, if somebody likes to print stuff or likes to open, a web page and look at that, that really need to
exist.
Need to exist first in the most way possible, in the best form, using the best infrastructure, search, and so on. And all of that, Discord and I don't know, chatbots, etc. This is okay. It's all nice and can be done, but first we need to deal with this. Yeah. It's my job. I'm actually hosting this.
Thank you. You had mentioned that you had gotten some feedback about our documentation. In that feedback, did anybody point to somebody that's doing it better? Is there an open source project?
Really good question. I think I actually removed some slides from last ZDS because with regards to things being more practical there. I would need to pull it up, but I mean, FreeRTOS was mentioned. Nothing more. I know for a fact that I'm looking to things like Riot OS for on the topic of specifically of boards and like answering this question, which comes quite often, which is your board supported in Zephyr? And maybe now with hardware model v2, we are in a way better place to do that. But like, is Nucleo blah 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 supported? Like, they have something that's arguably slightly better. Like, it only allows to search through a few criteria, but that I would be interested in improving. Don't know if Riot does it much better, but they have what's considered a good documentation, in my opinion. And there might be projects that have nothing to do with autosys, which we might want to look at too.
Yeah, this is, I think, something we tried to do multiple times. And I remember doing something like that. I showed you that, yeah. That's where actually infrastructure becomes relevant here. Because if you try to do that with Sphinx, that's probably, I don't know if that's going to work. Yeah, so we need to figure out how to go beyond the infrastructure that we have to provide this type of value, yeah? Actually, a relevant question to that is, for example, the APIs, yeah? And how we integrate API documentation in RST right now, and also provide the Doxygen information as well, and having discrepancies and having things out of sync and things documented in one place but not in the other place, and so on, yeah? So it's very important that at least, and probably that's actually one of the topics that need to be discussed in this forum is, and was discussed in the TSC meeting 2 days ago, is like APIs and documentation. I mean, do we actually want to go full scale on RST and try to describe everything in an RST, or do we want to use the power of Doxygen, which is we have, and you can do a lot of things in Doxygen that I think Riot.
I was going to look at him, and is already nodding his head to the point of we need more like context and what is the use of such or such thing. It probably doesn't start by the API. You need a higher level of talk about the concepts in more human, sort of like practical.
Yeah. Doesn't Riot actually still use Doxygen, or I mean, Riot?
I don't know. I never bothered checking. It looks like it could be. It looks like they might have everything in the Oxygen, actually.
Yeah, that's what I thought. Yeah, I thought they had everything
Yeah,
in
that
Doxygen.
looks very much like.
Yeah, and that's actually not bad at all.
Yeah, that's also an option, I guess.
Yeah, so it's something. I'm not saying go completely to Doxygen, but there are a lot of things that can be described, and then you have one single place for everything. But either way, yeah. So.
Yeah.
Thank you. So speaking of Doxygen, you can strike a balance, like you could have functions and struct definitions and some defines, and it integrates very well with RST. I don't know if it's being done currently like that. I know that that's slightly, different topic. Rust has pretty good documentation, and they do it in a twofold way. Like they have this Learn the Rust book and the actual documentation that, in my opinion, is very well written. And I don't know if it's the latest one. That's the book, actually.
Yep.
And the book is something I wanted to raise as well. Like, since I think that Zephyr is becoming like a good source of, maybe it's not as easy as, for example, Arduino to do stuff and teach in schools, for example, or in universities, but it's still quite accessible for many boards that have full support, and you could do many things. And but the problem is that some things are not straightforward. And if there was, for example, Rust does it very well. They have the Rust embedded book that guides you, like here is a LED, you do a Blinky, here is a GPIO, and you can, and it does it using as an example STM discovery board, which is a very accessible board. And I was thinking that maybe it could be a good idea to have some kind of a structured guide, which could be then, which would serve like the, I'm very new to programming / embedded, and I would like to start with this project.
Yeah. As opposed to the current documentation, which is more like reference documentation.
It is like for people who know a little bit about both programming and embedded electronics, so yeah.
What was that?
Is still working? Okay. My point is a bit different right now. Okay, we have some documentation. Going back to the beginning, Michael, you said that maybe it is your talk that the documentation may not align in one point with another. Are we actually, who is writing this documentation? Are developers? Are we actually trained to write good documentation? Do we know how to write good documentation? Are the maintainers like looking for the good documentation to be, okay, I want this documentation to be fixed, I want this to nicely integrate? I think that we have right now is like a mix of someone writing something, people that are not like really fluent on English, if we are talking about the English documentation. So I think we have a more fundamental problem. I'm not sure how to solve it, but maybe we should be aware of it.
Yeah, following this question, one thing that it's never really clear for me, it's what is the audience when we are writing documentation, right? I'm writing a documentation for a developer that is developing a new driver for Zephyr, or I'm writing the documentation for someone that is going to use, this subsystem or this part of Zephyr. So that it's also sometimes not clear,
Yeah, I don't know if there's a good answer to that. I think
I think the audience or the target audience really need to be clarified and need to be understood. Yeah, because as I was saying yesterday, or was yesterday, Zephyr is not a product. I mean, we are not trying to actually go and address a certain use case, etc. This is something that needs to be available for developers rather than, users. It should deal with users, but users in the sense of I'm using Zephyr to do something myself. Maybe I'm not contributing back, or I'm just turning an LED on, off, just to try things out. But it's not. The documentation should not go into the level of, hey, this is like a product that I bought, and this is the manual of how I use it. Yeah, that's because that goes into a completely different level. However, I think it has its benefits, but I don't know if we don't define our target, then we will have mixed variants of the documentation, similar to was said there, and there will be no consistency. And the problem that you described is that depending on the developer, the language in one single file will be completely different, and you might be talking not only like in the form of talking, you will be talking to two different peoples or persons in the same sentence sometimes if it's written by two different people. Yeah. We have 5 minutes, by the way, since
yes, I mean, I don't think. I mean, we can also switch gears to. I think I would love to do more around like surfacing the capabilities of like for all the boards and SoCs that we have supported in Tree. I think I don't want people to have to navigate like tons of DTS files to figure out whether such or such thing is supported. I think it's documentation worthy to surface that kind of information. Or to put it differently, I could pick virtually any board in Tree and look at this and double check with the reality, and then it would be just, so at a minimum, maybe we just need to get rid of that, because I'm not sure that's helping anyone, but thoughts?
Well, I see where you want to take this, and you want to have documentation that describes every feature that's supported by a given board, but that kind of shields the user from DTS, and DTS is so
at first, at least.
Well, yeah, I fear it's just gonna sort of delay.
But that's also shielding the user from DTS. You would agree? Like, what's the point of this then?
That gives you a quick overview of what's supported on this board. But if you want to dig into the details, I don't think we'll get much from auto-generating. We discussed this before, and auto-generating documentation based on the DTS from the board. I think I'd much rather have people dig into the DTS and try to get familiar with how that's done.
I think even before DTS, we wanted to auto-generate that, before we had DTS. And I don't think we ever agreed that the way it is right now, that DTS or auto-generating is the wrong idea. Yeah, it's just we didn't get to it. Yeah, we never got to it. I don't think this is describing. The problem with that, the first problem is this becomes out of date.
I'm pretty sure
so fast. Yeah. So either we provide something like this and we keep it updated, or we drop it completely. And if we want to keep that updated, the best way to do that is, and this is documentation, talking about the board. This is not talking about how do I write a driver and what the hell is DTS. Maybe at the end of the day, a user does not even have to look at DTS, because if you have to look at DTS and understand what DTS is, then maybe DTS is the wrong thing. So there are a lot of things that would be abstracted and described in a DTS that the user might not even care about. Yeah. So
well, this is back to the sort of with the user, but I would hope that some users, they don't have to care about DTS. Like they're actually going to write an application as just sensors are already enabled, blah, blah, blah. It's a dev kit. That's going to be their first 2 weeks into Zephyr.
Right,
DTS.
that's first 2 weeks.
Yeah.
But coming from your talk, Anas, Zephyr is not the product. Zephyr is just a framework. And if you want to use this framework, you're not going to use it on the development board. You're going to use it on the development board for finding out what kind of SoC are you going to base your product on.
Right,
So
but
eventually,
we want to enable,
eventually, if you're going to use Zephyr, you're going to have to learn about this.
Yeah, I think the problem that I'm trying to solve is I want to make sure that people actually get a chance to try Zephyr and are not scared away by being like, I don't know if it's supported, I don't know where to look to know if it's supported. I'm going to look someplace else, like another vendor, another whatever.
Yeah, but I mean, okay, so I think we are conflating the problem, or we are talking about something completely different. We are talking about documentation here, and I think basically this needs to be up to date if we are to document that and show that. And the best way to do this, if we have the capabilities, is to auto-generate that. And one second, yeah, and I'm not saying we shouldn't document how to use DTS and how to understand DTS and how to change DTS and so on. That's a completely different topic. Right now, I'm talking about a board which has supported features, and maybe I am looking for something that I want to experiment with. And this can actually be useful, yeah, because I look at this board or the multiple boards that we have, and I would actually go pick one that has the best support for devices and so on.
So it better be accurate what you're going to see.
And then, this is like the entry point. Then you can go deeper and start looking at how do I use DTS and so on and so on. So it's a different problem, yeah. Either we do that or not do it at all. Yeah, sorry.
I was just going to say, for auto-generating this, could we use the supported tag and the board YAML, right? We have this list of tagged items that, granted, as far as I can tell, aren't fully standardized. Tests just say, dependencies, so we'd have to standardize them to get this to work. But if we did, then that's literally a list of what's tested on the board right there. And if the board's not failing tests, it's safe to assume at least that the examples build.
Yeah, but this list is also out of sync most of the times, yeah. And actually, the idea was to use DTS to populate this list as well, instead of relying on the manually maintained, supported lists in a YAML file, which is for Twister, yeah. Anyways, we are out of time, yeah, just to let you know, because we have the next session.
We can continue the discussion in the Meet the Maintainers. Thanks, everyone, because that was actually super interactive. So,
Thank you.